Hello there, and welcome to Space Sleep Journey, where curiosity takes the gentle shape of a bedtime story and science moves at the pace of a quiet breath. I am so glad you are here tonight. There is nothing to do now and nowhere to be. You have already done enough today. All that is left is to rest and to wonder softly about something very far away. Tonight we will be wandering slowly toward one of the strangest and most wonderful questions in all of space. If a black hole is simply a place where gravity has won, a place where matter is squeezed so tight that not even light can climb back out, then how many different kinds of them are there drifting through the universe tonight? And what makes each one its own creature, from the smallest whisper born of a dying star to the giant sitting quietly at the center of our own galaxy, to the monsters heavier than all the stars of the Milky Way combined? We are going to meet the whole strange family of them one by one, slowly, and we are going to ask how we could ever come to know such dark and hidden things at all. But before we begin, I would like to wonder something about you. Where are you listening from tonight? Perhaps you are in a great bright city, where the glow of a million windows and street lamps washes the sky pale and the stars stay hidden behind it, so that you have to take the deep dark on faith. Or perhaps you are somewhere quiet and far from all of that, out where the night still turns truly black, where if you stepped outside and let your eyes adjust, the whole river of the Milky Way would spill overhead, thick with more stars than you could ever count. Wherever you are, bright city or quiet countryside, a warm bed or a long dark drive, we are under the same sky tonight, the same one that holds all the dark doors we are about to explore. And it is nice, I think, to know we are wandering through it together. If you find some peace in this quiet hour, I would be grateful if you tapped the like button or subscribe to the channel so that others who need a calm voice tonight can find their way here too. It is a small thing and it helps more than you might guess, and then you can set your device down and forget all about it. Now, take a breath. A slow one all the way in, and let it go, even more slowly than it came. Let your shoulders drop. Settle into your chair or your pillow and let your body grow a little heavier where it rests. There is no hurry now. We have all night, and we will take our time with every step of it. So imagine, if you would, that the night is clear and cool, and you are lying back in the soft grass of an open field, far from any town, far from any light but the stars. Above you, the sky is deepening, and the stars are coming out one by one, and then by the handful, and then in their thousands, until at last the whole great river of the Milky Way has spilled itself across the dark, from one horizon to the other, more of them than you could ever hope to count. The air is still. The grass is cool beneath you. And somewhere up in that spilled river of light, unseen, giving off no glow of its own, wearing the face of ordinary darkness, there is a thing as heavy as a star, or heavier still, a place where gravity has quietly won. You cannot see it, but it is there. And tonight, lying here beneath all of it, we are going to wander our way toward what it is. Let us begin with the gentlest possible idea, and let it settle over you like a blanket pulled up to the chin. A black hole is not a hole. That is the first thing to let go of tonight. The name makes you think of an opening in the ground, a pit, an empty place you could fall into and out the other side. It is none of those things. A black hole is a place where matter has been packed so tightly, squeezed so close upon itself, that gravity there has simply won. It has beaten everything else. It has beaten the pressure that holds a star up. It has beaten the light that would otherwise stream away. It has beaten the very idea of escape. Think of it this way. Everything you have ever known has a way out. A ball thrown upward comes back down, yes, but throw it hard enough and it could leave the earth entirely. That is what a rocket does. There is a speed for every world at which a thing can climb away and never return, and we call it the escape speed. On the Earth, that speed is about 7 miles every second, which is fast, faster than any car or plane, but still a number, still a thing a machine can reach. Now imagine a place where you would need to travel at the speed of light itself to climb away. And then imagine a place where even that would not be enough. That is a black hole. The escape speed there has climbed past the speed of light, and since nothing in the universe travels faster than light, nothing gets out. Not a ship, not a signal, not a single ray of light. The door only opens one way. That door has a name, and it is a name worth carrying with you through the whole of tonight, because we will return to it again and again. It is called the event horizon. Picture a still lake at night, and picture a boundary drawn on the surface of the water, a perfect circle, invisible, silent. Outside the circle, you can still paddle back to shore. Inside it, the current is too strong, and no matter how hard you row, you are going in. The event horizon is that boundary, drawn not on water, but on space itself. It is the point of no return. Cross it, and the story of your return is over. Not because something reaches out and grabs you, but simply because every path forward, every direction you could possibly move, now leads deeper in. That is the strangest part, and we will sit with it later. Inside the horizon, the center is not a place off to one side. The center is your future. It is where all roads lead. And here is a thing that surprises almost everyone the first time they hear it. The event horizon is not a solid surface. There is nothing there to touch, nothing to feel, no wall, no membrane, no shimmer in the dark. If the black hole were large enough, you could drift across that boundary and never know the moment you passed it. There would be no bump, no crossing sound, no sign. The universe behind you would still be visible for a while, and only slowly would you come to understand that there was no longer any way back. Hold that image gently. We will come back to it near the end when we talk about what it would truly feel like to fall. So, how big is this door, this event horizon? That is a fair question to ask early, and the answer is calm and clean, which is rare in a subject this strange. The size of the event horizon depends on only one thing, the mass, and there is a simple rule that connects them. The more mass you gather, the larger the door. This size has a name too. It is called the Schwarzschild radius, and we will meet the man behind that name in just a little while, because his story is one of the quietest and most moving in all of science. For now, only hold the idea. Every black hole has a radius, a reach, a size to its horizon, and that size grows in step with its mass. A small black hole has a small door. Giant one has a door wider than a solar system. Let me give you a number to hold, because numbers, said slowly, can be a comfort rather than a burden. Take our own sun, that great warm engine of light that has kept every living thing alive for as long as there has been anything alive to keep. The sun is enormous. You could fit more than 1,000,000 Earths inside it. And yet, if you wanted to turn the sun into a black hole, if you wanted to crush it down until gravity won and its light could no longer climb away, you would have to squeeze all of that mass, every bit of it, down into a ball only about 4 miles across. 4 miles. A little sphere you could walk around the edge of in an afternoon, holding within it the entire weight of a star. That is what it means for gravity to win. Not to add anything. To bring in more. Only to crush what is already there into a space so small that the ordinary rules of standing and pushing back simply give out. Now, the sun will not do this. It is far too gentle a star to ever become a black hole, and that is a promise, not a hope. The picture is worth keeping because it tells you the essential secret. A black hole is not about how much stuff there is. It is about how tightly that stuff is squeezed. Density is the whole story. You could, in principle, make a black hole out of anything at all, out of feathers, out of air, out of old letters, if only you could press them close enough. The universe rarely bothers with feathers. It uses the crushing weight of dying stars, and the slow gathering of gas over billions of years, and perhaps, at the very beginning of everything, the raw squeeze of the newborn cosmos itself. But the principle holds for all of them. Pack it tight enough, and gravity takes over, and a door opens that only swings one way. And this brings us softly to the single question that will carry us through the whole of tonight, the thread we will follow into sleep. If a black hole is simply a place where gravity has won, then how many different kinds of them are there, drifting through the universe tonight, each one quietly doing what it does? And what makes each kind its own creature, its own character in this long, dark story? 'Cause they are not all the same. That is the wonder we are walking toward. There is not one black hole repeated everywhere like a stamp. There is a whole family of them, a bestiary, ranging from the smallest whisper to the grandest monster, and each has its own way of being born, its own size, its own manner of hiding, and its own way of being found. Tonight we will meet them one by one, slowly, the way you might be introduced to the members of a very old and very strange family, and we will let each one settle in the mind before we move to the next. Before we meet them, though, there is one more idea to lay down, because everything that follows rests upon it, the way a house rests on its foundation. It is one of the most beautiful ideas in all of physics, and it has a curious name. It is called the no-hair theorem. Do not let the strange name trouble you. It means something simple and almost tender. It means that a black hole is one of the simplest objects in the entire universe. You are far more complicated than a black hole. A grain of sand is more complicated than a black hole. A single drop of the water in your glass tonight holds more detail, more history, more variety than the largest black hole in the sky. How can that be? Think of everything that goes into a star. Think of the countless atoms, the swirling currents of hot gas, the magnetic fields threading through it, the light pouring out, the slow churn of elements being forged in its heart. A star is a place of almost endless detail. Now let that star die and collapse and become a black hole. Nearly all of that detail simply vanishes from view. What is left, once the dust has settled and the horizon has formed, can be written down with only 3 numbers. Only 3. That is the no-hair theorem. It says that no matter what fell in, no matter how complicated it was, a black hole at rest is completely described by just 3 quantities. Its mass, which is how much matter it holds. Its spin, which is how fast it is turning. And its electric charge, which for reasons we will come to is almost always nothing at all. Sit with how strange and how clean that is. 2 black holes with the same mass, the same spin, and the same charge are not merely similar. They are identical in the deepest sense the universe allows. There is no way, even in principle, to tell them apart. No hidden mark, no secret history written on them, no scar from what they ate. A black hole made from a collapsed star and a black hole made, somehow, from an equal weight of old encyclopedias, if they shared those 3 numbers, would be the very same object. Everything else, all the richness and difference of what fell in, is gone, smoothed away, erased at the door. That is what the phrase means when physicists say a black hole has no hair, no stray features, no individuality beyond those 3 plain numbers. The simplest thing in a complicated universe. And this is why our whole journey tonight, this whole family of creatures we're about to meet, hangs on those 3 numbers. Because when you change them, you change the creature. Change the mass, and you move from a whisper to a monster, from something the weight of a mountain to something heavier than every star in a galaxy. Change the spin, and you move from a still, silent sphere to a churning whirlpool that drags the very fabric of space around with it. Change the charge, and you enter a strange country that the equations allow, but the real universe seems to avoid. 3 numbers. That is the entire alphabet. And out of that tiny alphabet, the cosmos writes every black hole there is. So let us begin to read. Let us start with the simplest member of the family, the one with the least to say for itself, and there is a gentleness in beginning with the plainest thing. This is the black hole that does not spin and carries no charge. Only mass and nothing more. 2 of the 3 numbers set to 0 and just the one left. Physicists call it the Schwarzschild black hole, and it is the purest, most perfectly round object the equations of gravity allow. A flawless sphere of darkness. No wobble, no lean, no motion, no turning. Just a still, silent well in the middle of space, with its one-way door drawn as a perfect circle around it. The name comes from a man named Karl Schwarzschild, and I want to tell you his story slowly because it is one of those true things that sounds almost too fitting to be real. In the year 1950, near the end of that year, Albert Einstein published the work of his life, the theory we call general relativity. It was a new way of understanding gravity, not as a force pulling across empty space, but as the bending and curving of space and time themselves. In this picture, a heavy object does not reach out and tug on you. Instead, it sinks a kind of valley into the fabric of the universe, and everything nearby simply rolls along the slope of that valley. The Earth does not pull the moon on a string. The Earth makes a dip in space, and the moon circles the rim of it like a marble rolling around the inside of a bowl. That was the idea. It was beautiful, and it was difficult, so difficult that Einstein himself thought it might be many years before anyone could find exact answers hidden inside his equations. He was wrong about that, and here is the moving part. Within only a few months, an exact answer arrived. And it arrived from the most unlikely place imaginable. Karl Schwarzschild was a German astronomer, already respected, already accomplished, and when the First World War came, he did not stay safe at a desk. He volunteered. He went to the front. And there, serving as a soldier, amid the mud and the cold and the artillery of that terrible war, he read Einstein's new theory, and he sat down and solved it. He found the exact shape of the space around a single round mass. He worked it out at the front, by hand, in the little time a soldier at war could steal for thinking. Then he sent his solution back to Einstein, who presented it on his behalf, and who wrote back with real astonishment that he had not expected anyone to reach such a clean answer so soon. And then the story turns, as the truest stories often do, towards sorrow. At the front, Schwarzschild fell ill with a rare and painful disease of the skin, one that his body could not fight off. He was sent home, but there was no cure, and in the year 1916, only a few months after he had solved the deepest equations of gravity in the middle of a war, Karl Schwarzschild died. He was 42 years old. He never saw what his solution truly meant. He never heard the words black hole, which would not be spoken for another half a century. He left behind a clean piece of mathematics, worked out under fire, and inside that mathematics, waiting quietly, was the first true description of the strangest object in the sky. When you hear the phrase Schwarzschild radius, the size of the event horizon, that is the man you are remembering. A soldier who did his greatest work in the dark, and did not live to see the dawn it opened. His black hole, the still and simple one, is where every student begins, and where our tour begins too. But here is the thing about the still Schwarzschild black hole. As perfect as it is on paper, the real universe almost never makes one. Because the real universe is turning. Everything spins. The Earth spins on its axis. The Earth circles the Sun. The Sun turns slowly on itself. The whole Milky Way rotates, a vast pinwheel taking hundreds of millions of years to come around once. Spin is everywhere, woven into everything, and when a spinning star collapses, the spin does not vanish. It concentrates. It speeds up. Think of a figure skater on the ice, arms flung wide, turning slowly, and then drawing those arms in tight against the body. What happens? The skater spins faster, far faster, without any push at all, simply because the same motion has been gathered into a smaller space. A collapsing star does exactly this, on an unimaginable scale. Its great girth pulls inward, and its slow turn winds up into a furious one. And so the black hole it leaves behind is not the still Schwarzschild sphere at all. It is spinning, and often spinning very close to the fastest that nature will permit. This spinning black hole has its own name and its own discoverer, and the finding of it is a story of a different kind, a story of patience rather than tragedy. For nearly 50 years after Schwarzschild, the world's finest minds tried to find the spinning solution, the answer for a black hole that turns. It resisted them. It was far harder than the still case, tangled and knotted in ways that defeated attempt after attempt. Half a century passed. And then, in the year 1963, a mathematician from New Zealand named Kerr found it. He worked it out, this rotating solution that so many others had failed to reach, and it was so elegant, so obviously right once seen, that it changed the study of black holes forever. To this day we call a spinning black hole a Kerr black hole, and because nearly every real black hole spins, the Kerr solution, not the Schwarzschild one, is the true portrait of the black holes that actually fill our sky. Now, what does spin do to a black hole? What makes the Kerr creature different from the still Schwarzschild one? Here we arrive at one of the most haunting ideas in all of physics, and I want you to picture it gently. A spinning black hole does not merely turn within space the way a top turns on a table. It grips space itself and drags it around. Fabric of the universe near a Kerr black hole is pulled into a slow, relentless swirl, wound around the hole like water circling a drain, and nothing nearby can stay still against it. This is called frame dragging. Imagine you are floating in space near a spinning black hole, and you decide to hold perfectly still to point yourself at a distant star and refuse to move. You cannot do it. Space beneath you is flowing, turning, carrying you along whether you wish it or not, the way a slow river carries a leaf even if the leaf tries to stay in one place. There is a region around a spinning black hole where standing still is simply not among the choices the universe offers you. You must turn with it. You are swept along by the current of space itself. Sit with that for a moment, because it is one of the deepest things we know. Space is not a fixed and empty stage on which events happen. It is a thing that can be bent and stretched, and near a spinning black hole it can be set turning like water in a whirlpool. The great physicists who first understood this could hardly believe it, and yet the mathematics was clean, and later the measurements agreed. Real black holes really do drag space around themselves. Some of them spin so fast that they approach the very limit. The fastest a black hole is allowed to turn before something would break. And all the while they sit there in the dark, silent, dragging the cosmos into a slow, eternal spiral around a door that only opens one way. So now we have two of our creatures. The still one, the Schwarzschild black hole, perfect and rare. The spinning one, the Kerr black hole, common and strange, winding space around itself. And you will remember that the no-hair theorem gave us three numbers, not two. Mass, Jahr, spin, and charge. So what of the third number? What of a black hole that carries an electric charge, the same kind of charge that clings to your hair on a dry winter day, or that snaps between your fingertip and a doorknob after you cross a carpet? Here the equations are perfectly willing. They allow it. A still black hole with charge has a name given to two physicists who worked it out, Hans Reissner and Gunnar Nordstrom, and so we call it the Reissner-Nordstrom black hole. And a black hole that both spins and carries charge, the most general kind the equations permit, holding all three numbers at once, is called the Kerr-Newman black hole, after Roy Kerr and a physicist named Ezra Newman. On paper, these charged black holes are as real as any other. They are honest solutions of the equations of gravity, worked out carefully and checked many times. And yet, here is the honest thing, and on this channel we always tell the honest thing gently as its own quiet kind of wonder. Charged black holes are almost certainly not out there. The universe seems to refuse to make them, or at least to refuse to let them last. The reason is beautifully simple. Space is not truly empty. It is thinly filled with gas and dust and drifting particles, and among those particles are ones that carry positive charge and ones that carry negative charge, in nearly equal measure everywhere you look. Now suppose a black hole somehow gathered up a strong positive charge. What would happen? Positive charge would push away other positive particles, and it would pull in negative ones, drawing them toward itself from the surrounding space. And as those opposite charges fell in, they would cancel the black hole's charge, neutralize it, bring it back to nothing. The universe, in other words, is constantly reaching out to erase any charge a black hole might collect, the way a glass of still water smooths itself flat after you lift your finger from the surface. And so, while the charged black holes live perfectly well in the equations, we do not expect to find them living in the sky. They are a country that the map allows, but the land does not seem to contain. And naming that gap plainly as a real and open question is part of the honesty of this whole story. We keep the charged ones in the family because the mathematics keeps them. We simply do not expect to meet one in the dark. Before we go on to meet the black holes the universe actually makes, it is worth pausing to wonder how human beings ever came to imagine such a thing in the first place, because the idea is far older than most people suppose, and its long, slow arrival is a gentle story in itself. You might think black holes were dreamed up in the last 100 years, alongside Einstein. The first whisper of the idea came much earlier, more than 200 years ago, from a quiet English clergyman named John Michell, who was also a gifted natural philosopher, one of the finest scientific minds of his day, though he is little remembered now. In the year 1783, long before anyone knew what light truly was, before there were any of the tools we have spoken of tonight, John Michell sat down and reasoned his way to something astonishing. He knew that a cannonball fired upward would rise and fall back, and that fired hard enough it might escape a world entirely, and that the heavier the world, the faster you would have to fire it to get away. And he asked a simple question that no one had quite asked before. What if a star were so massive and its gravity so strong that the speed needed to escape it was greater than the speed of light itself? Then, he reasoned, even light could not get away from such a star. It would rise a little and fall back, or never rise at all, and the star would be invisible, dark, its light forever trapped by its own weight. He called such an object a dark star, and he even suggested, with remarkable foresight, that we might detect one by watching how its gravity tugged on the visible stars around it, which is very nearly the exact method by which we found Cygnus X-1 2 centuries later. Country parson, with pen and paper and pure reason, had glimpsed the black hole 200 years before we photographed one. For a long time the idea slept. It was too strange, and light turned out to be more subtle than anyone in Michel's day understood, and his dark stars were quietly set aside and largely forgotten. It took Einstein's new picture of gravity and Schwarzschild's solution worked out at the front to bring the idea back to life in a firmer form. And even then, for decades, most scientists, including Einstein himself, did not really believe that nature would ever actually make such a thing. They thought the strange solution was a mathematical curiosity, a quirk of the equations, something that could exist on paper, but that some kindness of physics would prevent from ever forming in the real universe. Surely, they felt, a real star could never truly collapse all the way down to a point. Surely something would stop it. The turning came slowly through the work of many. In the late 1930s, two physicists worked out that a massive enough star really could collapse without limit once its fuel was gone, that nothing known could halt it, and that it would indeed crush itself down past the point of no return. And then, in the 1960s, a great flowering of understanding arrived, led by brilliant minds who proved, with deep and beautiful mathematics, that such collapse was not a fluke of perfect symmetry, but a robust and unavoidable feature of Einstein's gravity, that under the right conditions the forming of these objects was not merely possible, but inevitable. One of those thinkers showed that once collapse passes a certain point, a singularity at the centre is unavoidable, a genuine breakdown of the smooth fabric of space and time, and for that profound work he would, many decades later, be honoured with the highest prize in physics. The strange curiosity had become a firm prediction of the theory, and the sky, as we have seen, would go on to confirm it again and again. And it was in the middle of all this, in the year 1967, that the object finally got the name we now use. For a long time these things had been called by clumsy phrases: collapsed stars, frozen stars, dark stars, gravitationally completely collapsed objects, none of which stuck. Then a celebrated physicist named John Wheeler, in a lecture, used a short, vivid phrase that someone in the audience had reportedly suggested, and it caught fire at once and never let go. A black hole. 2 plain words, and suddenly the strange object had a name that a child could remember and that carried, in its very sound, some of the mystery of the thing. Within a few years, everyone was using it, and it is hard now to imagine the object called anything else. It is a small reminder of how much a good name matters, how a thing can wait 200 years, from a country parson's dark star to a firm prediction of the finest theory of gravity, and only truly enter the common imagination once someone gives it the right 2 words. So when you say the words black hole tonight, so easily, so familiarly, remember that they are younger than you might think, barely older than living memory, and that the idea behind them waited a very long time in the minds of a few patient people before the universe let us see that it had been making them all along. So we have the shapes a black hole can wear, still or spinning, charged or plain. But shape is not the same as size, and it is size, above all, that sorts this family into its true kinds. So let us come down now to the smallest of the real black holes, the ones the universe actually makes in great numbers, and let us ask how they are born. Because every black hole in this first group begins the same way. It begins as a star, and it begins with a death. Picture a star far larger than our sun, one of the calm, middle-sized stars like the one that warms our mornings, but a giant, a star with perhaps 10 or 20 or 30 times the mass of the sun. For millions of years that star does what every star does. Deep in its core it presses hydrogen together so hard that the hydrogen fuses into helium, and that fusion pours out a steady flood of energy that pushes outward. And all the while gravity is pulling inward, trying to crush the star down. A star's whole long life is really just this one quiet argument, held in balance. The push of fusion out, the pull of gravity inward. As long as the two stay equal, the star shines on, steady and calm, for age upon age. But fuel runs out. It always does. When the giant star has fused its hydrogen into helium, it begins to fuse the helium into carbon, and then the carbon into heavier things still, oxygen and neon and silicon, each stage faster than the last, each a shorter and more frantic chapter than the one before. Millions of years at the start now takes only thousands, then years, then days. The star is burning through the last of everything it has. And at the very end, in its core, it fuses its way up to iron. Iron is where the argument is lost. Iron is the ash at the bottom of the fire. When you try to fuse iron, it does not give energy back. It takes energy away. And so the moment the core of that great star turns to iron, the outward push simply stops. The fire that held up the star for its entire life goes out in an instant. And gravity, which has been waiting patiently all along, finally wins. Core collapses in about 1 second. In that 1 second, something larger than our sun falls inward upon itself faster and faster, and the outer layers of the star, no longer held up, come crashing down and then rebound in a titanic explosion we call a supernova. For a few weeks that single dying star can shine as brightly as a whole galaxy of ordinary stars combined, bright enough that people on Earth have written down the sight of them for thousands of years, new stars flaring in the sky where none had been before. But the explosion, for all its glory, is not the part of the story we have come for tonight. We have come for what is left behind at the very center, once the light has faded. 'Cause if the collapsing core is heavy enough, nothing in the universe can stop it. The stubbornness of atoms, pressure of packed neutrons. Ja, nothing. It falls, and it keeps falling, and it crushes itself down past the point where light can escape, and a new black hole opens its eye in the dark. These are the stellar mass black holes, the black holes born from dying stars, and they are the most numerous large black holes in the cosmos. Our own galaxy alone is thought to hold many millions of them, perhaps 100 million or more, scattered through it like dark seeds, most of them drifting alone and unseen. In weight they run from about 3 times the mass of the Sun, at the smallest, to a few tens of times the mass of the Sun at the largest. That is the whole range of this kind. 3 suns to perhaps 50. Small, as black holes go. The whispers of the family. And yet even the smallest of them holds more mass than 3 suns crushed into a ball you could tuck inside a city with a one-way door only a few miles wide. Small is a strange word to use for a thing like that. But, in the company we are about to keep tonight, small is exactly what they are. Now, how did we ever come to know these things exist at all? A black hole gives off no light, drifts alone in the dark. How could anyone ever point to a patch of empty-looking sky and say, there is a dead star crushed into a door that swallows light? The answer is one of the great detective stories of the last century, and it centers on a single object, the first black hole that humankind ever truly found. Its name is Cygnus X-1. The story begins with X-rays. You know X-rays from the doctor's office, the invisible light that passes through skin to show the bone beneath. Turns out, the sky glows in X-rays too in certain places, and in the early years of studying that glow, before we could even loft instruments properly above the air that blocks such light, astronomers began to map the brightest sources of X-rays in the heavens. One of the very brightest sat in the constellation Cygnus, the Swan, which you can find flying down the summer sky along the band of the Milky Way. Because it was the first strong X-ray source found in that constellation, it was given the plain and now famous name Cygnus X-1. And when astronomers looked closely at what sat in that spot, they found something that did not add up. There was a star there, a large hot blue star, and it was clearly circling something, swinging around an unseen partner in a tight and rapid dance, completing a full orbit in only about 5.5 days. From the speed and the size of that dance, they could weigh the hidden partner, the way you can judge the weight of a hammer thrower's hammer by how hard they must lean back to swing it. And the hidden partner was heavy. Far too heavy to be any ordinary dark star. Far too heavy to be a burnt-out cinder or a ball of packed neutrons, because there is a firm ceiling on how much such things can weigh before their own gravity crushes them. Unseen partner in Cygnus X-1 sat well above that ceiling, and it gave off no light of its own, and it was pouring out X-rays. There was only one thing it could be. A black hole. The dead heart of a giant star, pulling gas off its living companion, and heating that gas to millions of degrees as it spiraled in, until the gas screamed in X-rays on its way through the one-way door. For a long time the case for Cygnus X-1 was strong but not certain, and into that uncertainty stepped two of the most famous physicists of the age, and they did something delightful with it. They made a bet. In the year 1974, Stephen Hawking, who would become perhaps the best-known scientist in the world, wagered against his friend Kip Thorne, another towering figure in the study of gravity. And here is the lovely contrary thing. Hawking, who had spent his life studying black holes, bet that Cygnus X-1 was not one. He bet against the very object he was famous for. He explained his reasoning with real charm. He had put so much of his life into black holes that, as he put it, if it turned out they did not exist after all, at least he would have the consolation of winning the bet. It was a kind of insurance against heartbreak. If the black holes were real, he lost the wager, but kept the life's work. If they were not real, he lost the life's work, but at least won the bet. Either way, he could not entirely lose. The stakes were as gentle and human as the wager itself. Nothing grand. Just a light-hearted prize agreed between friends who trusted the numbers to settle it in time. And the numbers did settle it. Over the years that followed, the measurements of Cygnus X-1 only grew firmer, the weight of the hidden partner only more certain, the case only more airtight, until at last there was no honest way to deny what it was. And so, in the year 1990, Stephen Hawking conceded the bet. The story goes that he broke into Kip Thorne's office while Thorne was away, found the framed record of their wager, and marked it as lost with his own thumbprint for a signature, since by then his hands could no longer easily write. He had lost the bet, and he was glad to lose it, because losing it meant the black holes were real and his life's work stood. That is how the first black hole was found, and how the world came to believe in it. Not by seeing it, for it cannot be seen, but by watching what it did to the star beside it, and by weighing the invisible thing at the center of the dance. And there is a small, warm footnote to add, one that shows how living a science this still is. In recent years, astronomers measured Cygnus X-1 again, with far sharper tools than the 1970s could offer, and they found it was farther away than we had thought, about 7,000 light-years from Earth, and heavier than we had thought as well. The black hole in Cygnus X-1, that first one, the one Hawking bet against, is now measured at about 21 times the mass of the Sun. It has grown in our understanding decade by decade, even as it sits out there unchanged, doing exactly what it has always done, quietly swallowing the wind of the star it dances with, 7,000 years of light away. Let us slow down here, because we have arrived at the heart of the whole matter, and it is a question worth turning over slowly in the mind as you lie there in the dark. How do we know? How can anyone know? A black hole gives off no light. That is its very definition, the one unbreakable rule of it. It is the one thing in all the universe that hides perfectly, that offers the eye nothing at all, no glint, no glow, no edge, no shape. And yet we speak of them by name, we count their kinds, we weigh them, we map where they sit. How can we possibly measure a thing whose whole nature is to give us nothing to measure? This is the puzzle that took the finest minds a century to work around, and the way they did it is, to me, more wonderful than the black holes themselves. So let us walk through it, slowly, one method at a time. The first and oldest trick is the one that found Cygnus X-1, and it rests on a simple truth. You cannot see the wind, but you can see the trees bend. You cannot see a black hole, but you can see what it does to the things around it. A black hole is never truly alone in the way it seems. It sits in a galaxy full of gas and stars, and its gravity reaches out and pulls on all of it, and that pulling leaves marks we can read. So we do not look for the black hole. We look for the bending of the trees. We look for the mark. Consider what happens when gas falls toward a black hole. It does not simply drop straight in, the way a stone drops into a well. Because everything in space is moving, the gas swirls as it falls, and it gathers into a great flattened disk, spinning around the black hole like water circling the drain of a bath, only far faster and far hotter. This is called an accretion disk, and it is one of the brightest things in the entire universe. As the gas spirals inward, the inner rings must move faster than the outer rings, and so the gas grinds against itself, layer scraping past layer, and all that grinding heats it, the way rubbing your hands together warms them, only carried to an unimaginable extreme. The gas in the inner disk is heated not to hundreds of degrees, not to thousands, but to millions of degrees. And matter that hot does not glow with ordinary light, glows in X-rays, that same piercing light the doctor uses to see through skin. So the black hole, which is itself perfectly dark, wraps itself in a searing halo of X-rays as it feeds, and that halo we can see from thousands of light years away. Darkest thing in the sky betrays itself by the brilliance of what it is destroying. There is a strange poetry in that. The black hole cannot be seen, but its meal can, blazing on the very threshold of the door in the last moment before it falls through and is gone. That is the first method, the glow of the feeding disk. There is a second, subtler, and in some ways even more beautiful, and it is the one that lets us weigh the invisible thing with real precision. It is the method of watching the stars dance. Remember that gravity does not only pull gas, pulls stars too, whole stars, and if a star wanders near a black hole and does not fall in, it will instead be caught into orbit, swinging around the unseen mass again and again, held on an invisible leash. And here is the gift. From the shape and the speed of that orbit, we can weigh the thing at the center, precisely, without ever seeing it. A heavy thing at the center makes the star swing fast and tight. A lighter thing lets it drift slow and wide. So we watch the star, we time its orbit, we measure how fast it moves and how far it reaches, and from that alone the mathematics hands us the mass of whatever it is circling, even if that something gives off no light at all. This is not a trick that works only in theory. In the very center of our own galaxy, astronomers spent decades doing exactly this, patiently, night after night, year after year. They watched a small cluster of stars near the galactic center, and they tracked the motion of each one, plotting where it sat month by month, building up the shape of its path across the years. And one star in particular, a star that swings in very close to the center on a long looping orbit, gave the answer away. Whips around the central point at a truly staggering speed, thousands of miles every second at its closest approach, faster than almost any star ever measured, and it completes its long orbit in only about 16 years, a human span short enough that the patient astronomers actually watched it go all the way around and come back. From that one star's frantic dance, and from the dance of its neighbors, they weighed the thing at the center of the Milky Way. And the answer was a mass of about 4 million suns, packed into a space smaller than the orbit of that innermost star, giving off almost no light. There is only one thing it can be: a supermassive black hole sitting at the heart of our own galaxy. We will come back to that giant later and give it its proper name. For now, notice only how it was found. Not by seeing it, by watching the stars swing around the empty seeming place where it hides and letting their motion do the weighing. The scientists who led those decades of patient watching were honored with the highest prize in physics for it, because they had done something that once seemed impossible. They had weighed the darkness. Now let me give you a third method, And this one is perhaps the strangest and most elegant of them all, because it uses the black hole's own gravity to turn it into a kind of lens. You will recall that gravity, in Einstein's picture, is the bending of space. And light, travelling through bent space, must follow the bend. Light rays curve as they pass a heavy object, the way a straight road must curve when it crosses a hill. This means that a black hole, or any heavy thing, can act like a great lens in space, bending and gathering the light of whatever lies behind it. If a black hole passes in front of a distant star, the star's light does not simply get blocked. Instead, the black hole's gravity bends that light around itself and focuses it, so that for a while the distant star appears to brighten, sometimes into a smeared ring or a doubled image, as its light is bent around both sides of the unseen mass. We call this gravitational lensing, and it is astonishing to think about. The black hole, which swallows all the light that touches it, can also, with the light that merely passes nearby, act as a magnifying glass, brightening the stars behind it. And by watching a distant star suddenly brighten in just the way the mathematics predicts, and then fade again as the dark mass drifts on, we can detect a black hole that is not feeding at all, one with no glowing disk, one that would otherwise be utterly invisible, betrayed only by the way it bends the light of something far beyond it. There are gentler tools still, refinements upon these, and they are worth a quiet word because they show how patient and clever this science has become. When astronomers study the glowing gas around a black hole, they do not only measure how bright it is, they spread its light out into its colors, the way a raindrop spreads sunlight into a rainbow, and in that spread of colors they can read how fast the gas is moving, because motion shifts the colors ever so slightly, toward the blue when a thing rushes toward us, and toward the red when it rushes away. This is the same effect you hear when an ambulance passes, its siren dropping in pitch as it goes by. Light does the same thing, and by reading that shift in the light of the whirling gas, astronomers can measure how fast the inner disk is spinning, and from that speed, once again, weigh the thing at the center that is whipping it around so fast. And there is one more, subtler yet, with a lovely name. It is called reverberation mapping, and it works a little like listening for an echo to judge the size of a dark room. The bright inner region near a black hole flickers, growing brighter and dimmer as its feeding stutters. When it flares, that flash of light travels outward and, a little while later, lights up the gas farther out, which then flares in answer. By measuring the delay between the first flash and the answering glow, the tiny pause while the light crosses the gap, astronomers can measure the true distance across that region, because they know exactly how fast light travels, and a delay is simply a distance in disguise. In this way they map the unseen structure around a black hole by timing its echoes, reading the size of the place they cannot see by how long its light takes to cross it. Take a moment and let the whole picture settle, because it is a marvel of patience and indirection. We cannot see the black hole. We will never see the black hole itself, not truly, for there is nothing there to see. And so we have learned to read it in every other way. We read the X-ray scream of the gas it swallows. We read the frantic dance of the stars it holds in orbit. We read the bending of the light that passes it. We read the shifting colours of its whirling disk and the delayed echoes of its flares. Every one of these is a shadow cast by an invisible thing, and by gathering the shadows carefully over years, we build up the shape of what casts them. It is a little like coming to know a person you have never seen, only by the warmth of the chair they just left, the sound of their step in the next room, the way the room is arranged around where they must have stood. You never see them, but you come to know them completely. That is how we know the black holes. Not by light, which they refuse us, but by every trace they leave in the light of everything around them. And still, for all of that cleverness, there was one thing we could not do for the longest time. We could not hear them. We could read the marks a black hole left on the gas, and the stars, yes. Two black holes far out in the dark, with no gas around them and no stars circling close. Two black holes simply falling toward each other in the empty deep, left no such marks at all. They fed on nothing. They lensed nothing we happened to be watching. They were, in the fullest sense, silent and invisible together. To catch those, we would need an entirely new sense, a way of feeling the universe that no one had ever possessed. And in the year 2015, after 100 years of waiting, we finally grew it. To understand this new sense, this way of hearing black holes we could never see, we have to go back once more to Einstein and to a prediction he made, and then, for a while, doubted. When he first understood that gravity was the bending of space and time, he realized something further, something almost too strange to believe. If space itself can bend, then space itself can ripple. If a heavy thing moves, it should send waves out through the fabric of the universe, ripples in space and time, spreading outward like the rings that spread when a stone drops into a still pond. He called them gravitational waves. And then he worried that they might be too faint to ever matter, too small for any instrument, forever beyond reach. For a long time even he was not sure they were real, and not merely a quirk of the mathematics. Here is what such a wave actually does, and it is worth picturing slowly, because it is so gentle and so profound at once. When a gravitational wave passes through you, it very slightly stretches space in one direction and squeezes it in the other, and then the other way around, back and forth, as the wave rolls through. Everything is stretched and squeezed together. You, the room, the ruler you might try to measure with, all of it, because it is space itself that is changing, not the things in it. That is what makes it so nearly impossible to detect. The wave does not push against a fixed background. It changes the background. And the amount of the change by the time a wave reaches us from far across the universe is almost unimaginably small. It stretches and squeezes space by less than the width of a single atom, less even than the width of the tiny center of an atom, across a distance of miles. To measure that, is to measure a change smaller than anything human beings had ever measured before, by far. And yet we built a machine to do it. Two machines, in fact, one in the state of Louisiana and one far away in the state of Washington, so that a real signal from space would strike both, while a local tremor, a passing truck or a small quake, would rattle only one. Each machine is shaped like a great letter L, with two long arms stretching out for miles at a right angle to each other. Down each arm a beam of laser light races, bounces off a mirror at the far end, and races back, and the two beams are compared with fantastic precision. If a gravitational wave rolls through, it stretches one arm and squeezes the other by that impossibly tiny amount, and the returning light falls ever so slightly out of step, and the machine feels it. This vast, delicate instrument is called the laser interferometer, gravitational wave observatory, though everyone simply calls it by the shorter name, and it is one of the most sensitive things our species has ever made. It can feel a change in length 1,000 times smaller than the center of an atom. It can feel the shiver of space itself. For years it listened and heard nothing, which was expected, for the machine was being coaxed toward ever greater sensitivity. And then, on the September morning in the year 2015, only days after the improved detectors had been switched on, before the official search had even formally begun, a signal arrived. It swept through the Louisiana detector, and then, 7/1000ths of a second later, through the Washington one. Exactly the delay you would expect for a ripple crossing the country at the speed of light. And when the scientists looked at the shape of what they had caught, they saw something they had waited 100 years to see. A rising tone, a chirp, a wave that climbed in pitch and grew in strength over a fraction of a second, and then abruptly stopped. It was the sound, if you turned it into sound, of two black holes in their final moment, spiraling around each other faster and faster and closer, until they slammed together and merged into one and fell silent. Think about what that signal was. Somewhere out in the deep dark, more than 1 billion light years away, farther than the mind can truly hold, two black holes had been circling each other for ages, drawing slowly closer, shedding their energy into ripples of space as they went. One weighed about 29 times the mass of the Sun. The other weighed about 36. And in the final fraction of a second, they whirled around each other at nearly half the speed of light and crashed together, forming a single black hole of about 62 times the mass of the Sun. If you are doing the sum in your head, you have noticed something is missing. 29 and 36 make 65, not 62. Where did the other 3 suns' worth of mass go? They did not fall in. They were not left behind. They were turned entirely into the energy of the gravitational waves themselves. 3 whole suns' worth of matter converted to a burst of rippling space in a fraction of a heart. For that one instant, that single collision far out in the dark poured out more power than all the stars in all the galaxies of the entire visible universe, shining together, combined. And yet it made no light at all. Not a flicker. all of that unimaginable power went entirely into shaking the fabric of space, into the silent chirp that reached us 1 billion years later as a tremor smaller than an atom. And this is the wonder of it, the thing worth carrying with you into sleep. That collision happened more than 1 billion years ago. The waves it made set out across the universe when the Earth was young, when there was nothing here but single cells in a warm sea, no plants, no animals, no eyes to look up. For over 1 billion years those ripples travelled, spreading and thinning, crossing the empty deep, passing dead and living galaxies, until at last, on an ordinary morning, they reached a small blue world where a strange creature had, just in time, built a machine delicate enough to feel them pass. A few years earlier, and we would have missed it. The wave would have rolled through an Earth with no instrument to notice, and gone on into the dark unheard, as countless others surely have. But we were ready by the barest margin, and we felt it. And for the first time in the history of life on this planet, something here heard 2 black holes collide. We had, in that moment, grown a new sense. For all of history we had known the universe only by its light, by what the eye and the telescope could gather. Now we could feel it too, feel the trembling of space itself, and that changed everything. Because those 2 black holes had given off no light. There was no glowing disk of gas around them, no star to circle, nothing at all for the old methods to catch. They were the truly invisible kind, 2 dark masses falling together in the empty deep, and by every older means they would have merged and gone unnoticed forever. Only by hearing the shape of space could we know they had ever been there at all. The scientists who built that machine and led its long, patient work were given the highest prize in physics, as those who weighed the galactic center had been, because they too had done a thing that once seemed impossible. They had heard the darkness. And with this new sense, a whole hidden population of black holes, silent and dark and far away, suddenly became knowable, one chirp at a time. It is with this new ear, as we will see, that we would finally catch the most elusive kind of all, the long missing middle child of the whole black hole family. So let us return to our family, and to the way it sorts itself by size. We have met the stellar mass black holes, the whispers born from dying stars running from about 3 to perhaps 50 times the weight of the Sun. And we know from the heart of our own galaxy that there are giants out there too, black holes of millions of times the Sun's mass, which we will come to soon. But that leaves a strange and troubling gap in the middle. Between the small ones of a few tens of suns and the giants of millions of suns, there is an enormous empty stretch, a whole range of sizes, from about 100 suns up to 100,000 suns, where for the longest time we could find almost nothing at all. The middle children of the family seemed to be missing. We call the black holes that would fill this gap the intermediate mass black holes, and for decades they were among the great puzzles of the sky. It made no sense that they should be absent. Think of it. If the universe makes small black holes freely, and if it makes titanic ones at the centers of galaxies, then surely there ought to be plenty in between, the way there are not only babies and grown adults in the world, but every size of growing child as well. Where were they? The giants at galaxy centers had to come from somewhere, and one natural idea was that they grew up from smaller seeds, building themselves larger over cosmic time by swallowing gas and by merging with one another. If that were true, the middle sizes should be everywhere, the growing seeds caught part way up. And yet we struggled for years to find even one that we could point to with real confidence. It was one of those absences that nags at scientists, an emptiness where there ought to be plenty, a hole in the family portrait. There were hints over the years, teasing and uncertain. Now and then astronomers would find a source of X-rays in a distant galaxy that shone too brightly to be a mere stellar black hole, and they would wonder whether it might be one of the missing middleweights feeding away. Now and then they would peer into the dense heart of a great ball of ancient stars, a globular cluster, and think they saw the tug of something heavier than any single star at its centre. Every one of these hints was arguable. Every one could be explained another way. None of them settled the question. The middle of the family remained a rumour, a thing that ought to exist, that almost had to exist, but that no one could yet hold up to the light and name for certain. And this is where our new sense comes back into the story, the new ear that could hear the shiver of space. Because if two black holes, each of some tens of suns, were to fall together and merge, the black hole they would leave behind would land squarely in that missing middle, and the gravitational waves of their collision would carry the news to us, no matter how far away and how dark. We would not need to see a glowing disk. We would not need a star circling close. We would only need to listen and to catch the chirp. On the 21st of May in the year 2019, we caught it. A signal rolled through the detectors, and when the scientists worked out what had made it, they found the largest black hole collision that had yet been heard, and something more precious besides. Two black holes had merged, one of them about 85 times the mass of the Sun, the other about 66 times the mass of the Sun. And when they came together, they formed a single new black hole of about 142 times the mass of the Sun. There it was. At last. A black hole of over 100 suns, born in the very act of being detected, sitting right in the heart of the long empty gap. It was the first solid, undeniable member of the missing middle, the first intermediate mass black hole that no one could argue away. After decades of rumour and hint, the family portrait had its middle child, caught not by any eye but by the trembling of space itself. And the discovery carried a deeper surprise folded inside it, the kind that makes scientists lean forward rather than sit back. Remember how stellar black holes are born, from the collapsing cores of dying giant stars. Turns out, there is a range of masses in which a black hole simply should not be able to form that way. When certain very massive stars reach the end, they do not collapse cleanly into a black hole at all. Instead, they tear themselves completely apart in an explosion so total that nothing is left behind. No black hole, no cinder, nothing. This forbidden zone means that a black hole of, say, 85 times the Sun's mass should be very hard to make from a single dying star. And yet one of the two black holes in this collision sat right inside that forbidden range. So how did it come to be? The leading idea is quietly wonderful. Perhaps it was not born from a single star at all. Perhaps it was itself already the product of an earlier merger, two smaller black holes that had come together long before to make this larger one, which then found a partner and merged again. A black hole built up in steps, a family tree of mergers, each collision stacking towards something larger. If that is right, then here, caught in a single signal, was a glimpse of the very process by which the giants of the universe might slowly assemble themselves, one merger at a time, growing from whispers toward monsters across the ages. Still, honesty asks us to name where we truly stand, and I will say it plainly, in the calm way this whole night asks for. The intermediate mass black holes remain the least understood members of the entire family. We have this one clear detection and a handful of other candidates that are strongly suspected but not beyond all doubt. Compared to the small ones, which we count by the many, and the giants, which we have now actually photographed, the middle children are still known only in glimpses. We are confident they exist. We have finally heard one born. But how common they are, and where most of them hide, and exactly how the great giants are assembled out of smaller pieces, these are questions still open, still being worked, still waiting for more chirps to arrive across the dark. It is a rare and lovely thing in science to be able to point to the exact edge of what is known and say, here, just here, is where our certainty runs out and the mystery begins. The intermediate mass black holes sit right on that edge. And so, having met the missing middle, let us go on now to the giants themselves, the great ones that anchor the galaxies, including the one that has been sitting quietly at the center of our own the whole time we have been speaking. Now we come to the giants, and the register of our story changes. The way your voice drops a little when you speak of something truly vast. These are the supermassive black holes, and there is nothing in the family remotely like them. Where a stellar black hole holds a few tens of suns at the most, a supermassive black hole holds millions of suns, and the largest hold billions. Say those words slowly. Millions of suns. Billions of suns. Each one a single object, a single door, into which you could pour the entire mass of a small galaxy of stars. And here is the fact that ought to keep you quietly awake with wonder rather than let you sleep, though sleep is where we are headed. Almost every large galaxy in the universe has one of these giants at its center. Not some galaxies. Not the special ones. Nearly all of them. Every great spiral wheel of hundreds of billions of stars, every vast elliptical swarm, seems to have a supermassive black hole anchored at its heart, sitting at the very center of the whirl, as if each galaxy were built around a dark and heavy seed. That includes our own. That is the part I want you to hold most closely tonight. our galaxy, the Milky Way, the great river of stars you can see spilling across the darkest skies, the wheel of hundreds of billions of suns, in which our own small sun is one unremarkable grain far out toward the edge, has a supermassive black hole at its center. It has been there the whole time. Through all of human history, through every night anyone has ever looked up, it has been sitting there at the heart of everything, quiet, patient, unseen. And we did not know. For nearly the whole of our existence as a thinking species, we had no idea that the center of our own galaxy held a monster. We learned it only recently, within a single human lifetime, by the patient watching of those swinging stars we spoke of earlier. Its name is Sagittarius, a star, written with a little star symbol that we say aloud as the word star, and it sits in the direction of the constellation Sagittarius, which is where you must look on a summer night to face the true center of the galaxy. When you turn toward Sagittarius, low in the southern sky of a northern summer, you are looking straight down the long road to the middle of the Milky Way, and at the far end of that road, 27,000 light-years away, sits the giant. 27,000 light-years. Let that distance settle. The light leaving Sagittarius, a star tonight, the faint glow of the gas swirling near its door, will not reach the earth for 27,000 years. And the light we gather from it tonight, left when the last great ice age still held the northern world, when mammoths still walked, when the first human artists were pressing their painted hands against the walls of caves. That light has been crossing the dark for the entire span of human civilization and long before, and it arrives only now. And how heavy is this thing at the center of our home? About 4 million times the mass of the sun. 4 million suns crushed together into a single dark point sitting at the middle of the wheel. And yet, and this surprised even the astronomers, it is a quiet giant. It is not feeding much. It has, it seems, largely cleared out the gas from its immediate neighbourhood over the ages, and so it sits there mostly calm, taking only the occasional small meal, glowing only faintly compared to what it could be. If it were feeding hungrily, gorging on a great flood of gas, it would blaze as one of the brightest things in the entire sky, a beacon visible clear across the universe. Instead it rests, quiet and dim, a sleeping giant at the center of our galaxy, and that quietness is part of why it took us so long to find it, and part of why we can study the stars swinging so close around it without their being swallowed or scorched. For a moment, standing at the center of the galaxy, if you somehow could, in the crowded neighborhood around Sagittarius, a star. The sky there would be nothing like ours. Here on the quiet outskirts, our night holds a scattering of stars, a few thousand visible to the eye, spread thin across the dark. There, near the center, the stars would be packed so densely that the whole sky would blaze with them, a million points of light where we see one, the night never truly dark, the heavens crowded shoulder to shoulder. And through all that blazing crowd, the stars nearest the center would be moving, visibly swinging around the unseen giant on their tight, fast orbits, some of them tearing around at thousands of miles a second, whipped along by 4 million suns worth of gravity concentrated into a dark point smaller than our own solar system. That is the heart of our galaxy. That is where all the roads of the Milky Way lead, if you follow them inward. To a bright and central sun, as an older imagination might have guessed, but to a dark and silent giant, around which the entire vast wheel of stars, our own sun among them, endlessly turns. For yes, we turn around it too. Our sun, carrying the Earth and all of us along with it, is circling Sagittarius, a star at this very moment, sweeping through space at about 500,000 miles an hour, out here on the quiet rim, far from the crowded center. And even at that tremendous speed, we are so far out that a single trip around the galaxy takes us more than 200 million years. The last time our sun was in this same spot on its long orbit, the dinosaurs had not yet come into their great age. We have gone around the giant only a score or so of times in the whole life of the sun. It is the slowest, grandest circle any of us will ever be part of, a turning so vast and so slow that no one will ever feel it, and yet it is real, and the giant at the center is what holds us to it, the still dark anchor of the entire spinning wheel. There is a deep and open question folded into all of this, and it is worth naming gently as we go, in the honest way this night asks for. We do not fully understand how these giants came to be. A stellar black hole we understand well enough, born from a dying star. But a black hole of 4 million suns, or of billions of suns, cannot form from any single star. There is no star that large. So they must have grown, gathering mass over the long ages, swallowing gas, merging with other black holes, building themselves up from smaller beginnings, perhaps from the very middle children we met a moment ago, the intermediate mass seeds. And here is the puzzle. When we look far out into the universe, and therefore far back in time, we find that some of these giants were already enormous when the universe was still very young, far too young, it seems, for them to have grown so large by the slow gathering we understand. How they came to be so big, so fast, is one of the real open questions of modern astronomy, a genuine mystery still being worked, not yet solved. We know the giants are there. We know roughly what they weigh. But how the universe built them, so many, so quickly, so long ago, is a thread that is still being followed into the dark. And that, I think, is one of the loveliest things about all of this, that even the largest, heaviest, most anchored objects in the cosmos still hold a secret about their own beginnings that we have not yet learned to read. For all that we had learned to read the black holes in the marks they left, in the X-rays and the swinging stars and the trembling of space, there was one thing we had never done, and for a long time it seemed we never could. We had never seen one. Truly. Not a picture of the thing itself, or rather of the darkness at its heart, ringed by the light it bends. To photograph a black hole seemed impossible, and for a simple reason. Even the giants, for all their vast mass, are small in the sky because they are so terribly far away. To take a picture of the shadow of Sagittarius, A star, 27,000 light-years off, would be like trying to photograph a single small fruit resting on the surface of the moon from here on Earth, and to see it clearly. No single telescope that could ever be built would be large enough. To gather that much detail, you would need an eye as wide as the Earth itself. So they built one. Not literally a single dish the size of the planet, for that cannot be done. But something just as good, and in a way more wonderful. Astronomers took radio telescopes, great dishes scattered all across the world, in the deserts of the American Southwest, on the high dry plateaus of Chile, in the ice at the very South Pole, in Spain, in Hawaii, in Mexico, and they made them all look at the same black hole at the same time, on the same night, their measurements stamped with the ticks of atomic clocks so precise that the separate recordings could later be woven together as though they had all come from a single instrument. When you link telescopes across the whole width of the Earth in this way, and combine their light with exquisite care, they behave, for the purpose of sharpness, like one titanic telescope as wide as the distance between them. As wide, that is, as the planet. They called this planet spanning virtual instrument the Event Horizon Telescope, named for the very thing it was built to see, the one-way door at the edge of a black hole. An eye the size of the Earth, made of many eyes, opened for the first time. The mountain of data was so vast it could not be sent over any wire. The recordings from each far-flung dish had to be flown, on stacks of hard drives, physically carried across the world to be combined in one place, and the drives from the South Pole could not even be shipped out until the long polar winter ended and the first planes could land again. Then more than 200 scientists at dozens of institutions around the world spent years turning that ocean of raw signal into a single image, working with enormous care, checking and cross-checking, 4 separate teams processing the same data without speaking to one another, so that if they all arrived at the same picture, no one could say it was merely what they had hoped to see. It was patience of a kind that is hard to imagine, years of it, all pointed at making one photograph. They pointed this Earth-sized eye first, not at our own giant, but at a larger and steadier one, in a galaxy called Messier 87, which sits about 55 million light-years away. Its black hole, which we call M87 star, is a true monster among the giants, about 6.5 billion times the mass of the Sun, and so large across that its door would swallow our entire solar system many times over. Because it is so vast, the gas around it moves more slowly and steadily over days rather than minutes, which made it an easier first subject to hold still long enough for a picture. And in the year 2019, the Event Horizon Telescope team unveiled what they had made. It went around the world in an instant, onto the front page of every newspaper, into the eyes of billions of people. The first image ever taken of a black hole. And what did it show? A ring of fire around a circle of perfect dark. A blurry, glowing, lopsided orange ring, brighter along its bottom edge, wrapped around a round pool of blackness at the center. The dark center is the shadow of the black hole, the region from which no light can reach us, the silhouette of the one-way door itself, cast against the glow of the hot gas swirling all around it. The bright ring is that glowing gas, its light bent by the black hole's gravity and wrapped around the shadow, so that we see the light from behind the black hole and around its sides all curved toward us into a circle. It was fuzzy. It was humble to look at. It was not the sharp and dramatic thing the movies had trained us to expect. And it was, for exactly that reason, one of the most profound photographs ever taken, because it was real. It was not a painting, not an artist's impression, not a simulation. It was an actual image of the actual shadow of an actual black hole, 6.5 billion times the mass of the Sun, 55 million light-years away, gathered by an eye the size of the Earth. For the first time, humankind had looked a black hole in the face, and the black hole had looked back with a single dark and steady eye. And then, 3 years later in the year 2022, the same team turned their planet-sized eye toward home and gave us the portrait we had most longed for. The first image of Sagittarius, a star, the giant at the center of our own galaxy. This one was far harder to make, and the reason is oddly beautiful. Our own black hole is much smaller than the monster in Messier 87, and so the gas around it whips around not over days but in mere minutes. Trying to photograph it was like trying to take a clear picture of a child who will not stop fidgeting, where the great giant in the other galaxy had sat as still for its portrait as a patient old man. The gas around our black hole rearranged itself even during the single night of observing, so that the team had to work out clever ways to capture the true underlying shape beneath all that flickering motion. They did it. And there it was, our own giant, the dark heart of the Milky Way, shown at last as a ring of light around a shadow, the same haunting shape as before. 4 million suns, 27,000 light-years away, sitting quietly at the center of our home galaxy, and now, for the first time, pictured. Thing that had been hidden since before our species had a name, brought into the light of an image that a child could hold up and look at. Take a moment to feel the whole arc of what that means. For nearly all of human history, a black hole was not even an idea. Then it was only a strange possibility hidden in the mathematics of a dying soldier's equations. Then it was a name whispered over an X-ray source in the constellation of the Swan, argued over in a friendly bet. Then it was weighed by the dance of stars and heard as a chirp in the trembling of space. And finally, in our own time, in these last few years, it was seen, its very shadow photographed against the fire of its own feeding, first in a distant galaxy and then in the heart of our own. From an impossibility to a rumor to a portrait, all within a single long human lifetime. That is how young this knowledge is. Pictures on which we now gaze so calmly did not exist when many of us were already grown. We are among the first people in all of time who have been able to look at an actual image of a black hole and know it for exactly what it is. Now that we have seen the first true portraits, let us linger a moment on what it would actually look like to draw near one of these things, because the sight would be unlike anything in ordinary experience, and it is a wonder worth picturing slowly as you lie there. We tend to imagine a black hole as a simple round patch of black against the stars, like a hole punched in the sky. The reality, worked out carefully from the equations and confirmed by that photograph of Messier 87, is far stranger and far more beautiful, because a black hole does not merely sit against the background, bends the background around itself. Remember that light rays curve as they pass a heavy thing, following the bend in space. Near a black hole, this bending becomes extreme, so extreme that light can be turned right around. And this does something remarkable to the view. If you were floating near a black hole with a glowing disk of gas swirling around its middle, you would expect, naturally, to see the near part of the disk in front and the far part hidden behind the black sphere, the way the far side of a plate is hidden when you hold it edge on. But that is not what you would see. The black hole's gravity would bend the light coming from the far side of the disk up and over the top and down around the bottom, curving it toward your eye, so that the back of the disk would appear lifted into view above and below the black sphere, as though the disk had been folded up around it like a halo. You would see the far side of the disk arching over the top of the black hole and curving under its bottom at the same time, an impossible-looking arrangement, the gas seeming to wrap completely around the darkness. Nothing would be hidden behind it. The black hole would gather the light from all around and drape it over itself like a shining shroud. And closer in, right at the edge of the shadow, something even stranger happens. There is a special distance from a black hole where light itself can be bent so severely that it is forced to travel in a circle, orbiting the black hole again and again before either falling in or escaping. Think of that. Light, the fastest thing there is, caught into orbit, going round and round the darkness like a moon around a world. This region is called the photon ring, and it means that some of the light reaching your eye from near a black hole has actually looped around the hole one or more times before coming to you, carrying an image of whatever lies on the far side, or even an image of the scene behind your own head, wrapped around and delivered from the front. Around the dark shadow there would glow a thin, intensely bright ring, sharper and brighter than the rest, made of light that has circled the black hole on its way to you. In that bright thin ring is folded, in principle, a distorted image of the entire universe around the black hole, wrapped again and again into an ever thinner band right at the edge of the dark. It is one of the most extraordinary optical effects in all of nature, and it is perfectly real, and a faint trace of it is thought to lie within that first blurry photograph we took. There is a related wonder that appears when a black hole passes precisely in front of a distant star, and it is so lovely that it earned a special name long ago. If the alignment is perfect, the black hole's gravity bends the star's light around every side of itself at once, and instead of a single point of starlight, you would see a complete glowing circle, perfect ring of light surrounding the dark, formed from the single star behind, its light gathered and bent around the black hole in every direction, and delivered to you as a halo. This is called an Einstein ring because Einstein's own theory predicted it, and we have since seen such rings in the sky, formed by the bending of light around distant galaxies and clusters. A single point of light, spread by gravity into a perfect circle. The universe, it turns out, is full of these gentle lenses, quietly bending the light of the far things around the near ones, and a black hole is the most extreme lens of all. So set aside, if you will, the simple picture of a black patch on the sky and hold this richer one instead. A sphere of perfect darkness, ringed by a bright thin band of light that has orbited it, wrapped in the folded-up image of its own glowing disk, draped impossibly over the top and under the bottom, the whole background of stars smeared and bent and doubled around its edges, everything near it distorted into arcs and rings by the sheer curving of space. Would not look like a hole at all. Would look like a place where the universe itself had been gathered up and knotted, where all the light for a great distance around had been caught and bent and made to dance in circles. Even the darkness at the centre would not be truly the black hole itself, but only its shadow, the region from which no light can reach you, printed against the glow of everything it has bent. That is the true face of the thing, not an absence. A distortion so complete that it becomes, in its own way, one of the most intricate and beautiful sights the cosmos can offer, if only there were ever an eye close enough and safe enough to see it whole. We have called the supermassive black holes giants, and so they are. But even among giants, there are giants. And now we come to the very largest black holes known, the ones that sit so far beyond the rest that they deserve a word of their own. Some call them ultramassive, the heaviest of the heavy, black holes not of millions of suns, but of tens of billions. And to meet the grandest of them, we must travel further out into the universe, and therefore further back into time, than anything we have yet spoken of tonight. There is an object far out in the dark that carries the plain and unlovely name Ton 618. Does not sound like much, that catalogue number, and yet it may hold within it one of the most staggering things ever measured. Ton 618 is a quasar. And to understand what that means, you have to understand what a supermassive black hole becomes when it is not resting quietly, as ours does, but feeding, gorging, swallowing gas at a tremendous rate. All that gas, spiralling in, grinding against itself, heats to such a fury that it blazes with light, and a feeding giant can pour out more light from the region around its door than all the hundreds of billions of stars in its entire galaxy combined. We call such a blazing object a quasar, and it is, in truth, simply a supermassive black hole caught in the act of a great meal, shining across the whole width of the universe on the strength of what it is destroying. The light does not come from the black hole itself, which gives off nothing. It comes from the doomed gas in the last bright moments before it falls through the one-way door. Ton 618 is one of the brightest and most distant quasars we know, and its light has been travelling toward us for something on the order of 10 billion years, so that we see it not as it is now, but as it was when the universe itself was young, only a few billion years old. And when astronomers study the light of that blazing gas and read from the way it moves how much mass must be at the center whipping it around, they arrive at a number so large it strains the mind. The most widely quoted estimate, worked out from the width of certain lines in its light, puts the black hole at the heart of Ton 618 at around 66 billion times the mass of the Sun. 66 billion suns in a single object, in a single door. Let me try to make that number felt rather than merely heard, because on its own it simply slides past. Our entire Milky Way galaxy, the whole vast wheel of hundreds of billions of stars, has a total starlight mass that, by the larger estimate, this one black hole would rival or exceed. That is the image to hold. A single black hole that may weigh as much as, or more than, all the stars in an entire galaxy put together. Not a galaxy's worth of stars spread out across 100,000 light-years of glittering space, but one dark point, one door, holding a comparable weight all by itself. And its reach is as staggering as its mass. The event horizon of a black hole that large, the one-way door itself, would stretch across a span many times wider than our entire solar system, so wide that light, which crosses from our Sun to the Earth in about 8 minutes, would take the better part of a day merely to cross the width of this single black hole's door. You could set our whole planetary system, the Sun and all its worlds, out to the most distant and frozen, inside that horizon many times over, with room to spare. And here, as always on this honest journey, we must name plainly where certainty ends. That figure of 66 billion suns is not beyond dispute. Comes from reading the motion of gas at a distance of 10 billion light-years, which is a delicate thing to do, and different methods give different answers. A more recent analysis, using improved techniques, revised the mass downward towards something closer to 40 billion times the mass of the Sun. Now 40 billion is still an almost unthinkable number, still enough to place Ton 618 among the very heaviest black holes ever found, still enough to rival a large fraction of a whole galaxy's stars. But it is meaningfully less than 66 billion, and the honest thing to say is that we do not know which figure is closer to the truth. The mass of this most monstrous of black holes is genuinely uncertain, disputed between something near 40 billion and something near 66 billion suns, and good scientists hold both numbers in mind and wait for better measurements. That uncertainty is not a weakness in the story. It is the story told truthfully. We are weighing a thing 10 billion light-years away by the flicker of the gas it is swallowing, and the marvel is not that we are unsure of the last digit, but that we can weigh it at all, that we can look across nearly the whole span of the universe and say, with any confidence, that here is a dark point as heavy as a galaxy. Sit for a while with the sheer strangeness of Ton 618, because it is worth the wonder. 10 billion years in the past, a single object was quietly, or rather furiously, holding within itself a weight to rival every star you could ever hope to see. And it was announcing itself across the entire universe, blazing with the light of its own great feast, brighter than a galaxy, so bright that we can catch its glow after 10 billion years of travel through the expanding dark. When that light set out toward us, there was no Earth. There was no sun. The gas and dust that would one day become our solar system had not yet gathered. The atoms that make up your body tonight were scattered who knows where, inside other stars, or drifting in clouds between them. And all that while, this light from the monster has been crossing the widening deep until at last it falls into our telescopes, and we read in it the weight of a galaxy held inside a single door. These greatest black holes are, in a sense, the far edge of the whole family we have been touring. We began with the whispers, the stellar black holes of a few suns, born from single dying stars. We passed through the long missing middle children of 100 to 100,000 suns. We met the giants of millions of suns anchoring the galaxies, our own among them. And now, at the grand far end, we find these monsters of tens of billions of suns, quasars blazing in the young universe, doors wider than solar systems, each one as heavy as the stars of an entire galaxy. It is one family, one kind of object, one simple idea, a place where gravity has won, and yet it runs across such a fantastic range of sizes that the smallest and the largest hardly seem like the same sort of thing at all. From a ball you could walk around in an afternoon to a door that light needs a day to cross. All of them black holes. All of them built from those same 3 plain numbers. And there is one more kind still to meet, the strangest of all, and the only one we have never actually found. There is one more thing the great feeding black holes do, and it is perhaps the most surprising of all, because it seems to run against everything we have said about them. We have called a black hole a place from which nothing escapes, a one-way door, a swallower of light. And yet the feeding giants are also, in a strange and roundabout way, among the great lighthouses of the universe, capable of flinging matter and energy back out across distances that beggar the imagination. Not from inside the door, of course. Nothing comes back from inside the door, but from just outside it, from the whirling superheated disk and the fierce magnetic fields wound around it. Some feeding black holes launch 2 enormous jets, beams of matter fired out from their poles at very nearly the speed of light, reaching not for miles, not for millions of miles, but for thousands and even millions of light years out into space, far beyond the edges of their own galaxies. Picture that. A supermassive black hole at the heart of a galaxy, dark and silent in itself, and yet from the region just around it, 2 thin, brilliant beams shoot straight out in opposite directions, punching clear through the galaxy and far beyond, straight and narrow and shining, so long that a single one of these jets can stretch farther than the entire width of the galaxy that launched it. The galaxy in Messier 87, whose black hole we photographed first, has exactly such a jet, a great blue-white beam thousands of light years long, and it was actually seen and recorded more than 100 years ago, long before anyone knew what a black hole was, long before anyone could have guessed that this strange straight ray of light was being fired out from the very edge of a dark giant 6.5 billion times the mass of the Sun. We looked at that jet for a century without understanding its engine. Now we know. It is the black hole, or rather the fury just outside it, hurling matter back into the universe with a force nothing else can match. How can a black hole, of all things, fling matter outward? Honest answer is that we do not understand every detail, and that is worth saying plainly, but the broad picture is becoming clear. It is not the black hole itself that does the flinging, but the violent, twisted, magnetized region of the inner disk, where gas spirals in at close to the speed of light through fields of tremendous strength. Some small part of the infalling matter, instead of crossing the door, is caught up and channeled by those wound-up magnetic fields and flung out along the poles, like water squeezed from a fist, accelerated to nearly the speed of light, and beamed far out into space. The black hole is the engine at the center, its immense gravity powering the whole whirling machine, but the matter that escapes never actually crossed the horizon. It only came near and was thrown back out by the storm at the threshold. It is as though the door, in the very act of feeding, sprays a fine mist of what it is eating far back over its own shoulder. These jets are among the ways the giants shape whole galaxies and even whole clusters of galaxies over the ages. When a jet plows out into the thin gas that fills the space around and between galaxies, it heats that gas and pushes it and stirs it, and in doing so, it can slow or halt the forming of new stars across an enormous region, because stars are born from cool gas, and a jet keeps the gas hot. So the dark giant at a galaxy's heart, through these beams, can reach out and touch the fate of stars that are trying to be born tens of thousands of light years away. The center speaks, and the whole galaxy listens. It is one of the deepest lessons of modern astronomy that the great black holes are not passive pits sitting quietly at the centers of things, but active shapers of the universe around them, their influence reaching far beyond the tiny region of the door itself, out across the galaxies they anchor. And when one of these jets happens to be pointed almost directly at the Earth, so that we are staring straight down the barrel of it, we see something especially fierce and bright, a source that can flare and brighten wildly, its light beamed right toward us. Astronomers have their own names for these various views of feeding giants, quasars when we see the blazing disk, and other names for when the jet points our way. But they are all, underneath, the same kind of object. A supermassive black hole, feeding, and lit up by the fury of its own feeding. It is a strange and humbling thought that the very brightest steady beacons in the entire universe, objects we can see across nearly its whole width, across 10 billion light-years and more, are powered by the darkest things it contains. The blackest hearts make the brightest lights. Out of the places where gravity has won most completely, where not even light escapes, comes some of the most brilliant radiance in all of creation, pouring out from the last bright edge of the door. There is a kind of poetry in that pairing that I never tire of. The darkness and the brilliance are not opposites here. They are two faces of the very same thing. There is one more way the giants announce themselves, and it is among the most dramatic events in the entire sky, though it unfolds so slowly over months that no eye could ever catch it in a single glance. It happens when an ordinary star, going about its long life, wanders too close to the supermassive black hole at the center of its galaxy. Most stars near a galactic center circle safely, held in wide, steady orbits for ages, the way our own sun circles at its great safe distance. Now and then, over the long turning of the ages, some star is nudged onto a path that carries it in too near, and when that happens, the giant does something terrible and beautiful at once. Pulls the star apart. We met this stretching force earlier when we spoke of falling in, the way gravity pulls harder on the near side of a thing than the far side, stretching it long and thin. For a person falling into a small black hole, that stretching is deadly. For a whole star wandering near a supermassive giant, the same force on a vastly larger scale is enough to overwhelm the star's own gravity, the gravity that holds it together as a ball. As the star sweeps in close, the giant's pull on the near side becomes so much stronger than its pull on the far side that the star is stretched out of its round shape, drawn into a long, thin streamer, and then torn apart entirely, unravelled into a ribbon of hot gas. Astronomers, with their gift for the vivid, sometimes call what follows a tidal disruption, but the planar image is truer to the thing. A star pulled into spaghetti and then flung in a long, bright arc around the darkness. And here is what makes it something we can actually see across hundreds of millions of light years. When the star is torn apart, only some of its gas falls straight in through the door. The rest is flung around the black hole and gathered into a sudden blazing disk, and as that fresh flood of stellar gas spirals in and heats up, the black hole, which may have been sitting quiet and dark and unfed for ages, suddenly flares to brilliant light. A galaxy centre that had been dim for a human lifetime, or for 1,000 human lifetimes, abruptly brightens, sometimes to shine as brightly as billions of ordinary stars, and then, over the following months and years, slowly fades again as the last of the shredded star is consumed, and the giant returns to its long quiet. We have caught many of these flares now, sudden brightenings at the centres of distant galaxies that swell and fade in just the way the tearing apart of a star would predict. Each one is the death cry of a single star, written in light across the dark, the last bright signature of a sun that wandered too close and was unmade. There is something solemn in it, and I do not want to pass it by too lightly, even on a night meant for rest, because it is a true part of the family's story. A star is a vast and ancient thing, a great ball of fire that may have shone steadily for billions of years, that may have warmed worlds of its own, and in a matter of days the giant at its galaxy's heart can undo all of that, unspool it into a ribbon and swallow the greater part of it forever. It is the largest and most complete kind of destruction the ordinary universe offers. And yet, held in the wider view, even this is part of the slow turning of things, part of how the giants feed and grow, part of the great cycle in which stars are born and shine and, in one way or another, at last give themselves back. The star that is torn apart does not simply vanish into nothing. Some of it falls through the door, yes, added forever to the dark mass of the giant. Much of it is flung back out, hot and bright, sprayed across space, its atoms scattered once more into the galaxy to drift and cool, and someday, perhaps, gather into something new. Even in this, the most violent of endings, there is a kind of return, a giving back, a scattering of the old star's substance into the long, slow story from which new stars and worlds are made. So the giants are not only anchors and lighthouses, they are also, now and then, the place where a wandering star meets its end, and in that ending briefly lights the darkness for all the universe to see. It is a rare fate. In the whole life of a galaxy, only a small number of its countless stars will ever wander close enough to suffer it, and our own sun, far out on the quiet rim, will never come anywhere near that danger. We are safe, out here in the calm suburbs of the Milky Way, 27,000 light-years from the giant, circling it gently and forever at a distance that means no harm. But somewhere out in the deep tonight, in some far galaxy, a star is drawing too close to a dark center, and beginning, slowly, over the coming months, to shine one last time as it comes undone. And its light, when it finally reaches us, ages hence, will tell us the whole quiet story, written in a slow, bright flare against the dark. Every kind of black hole we have met so far, from the smallest whisper to the grandest monster, has one thing in common. Every one of them was born late, so to speak, born from something that already existed. The stellar black holes were born from stars, and stars themselves took long ages to form after the beginning of the universe. The giants grew from those, or from seeds like them, gathering mass across billions of years. All of them are, in a sense, children of a universe that had already been running for a long while. But there is a kind of black hole that, if it exists at all, would have been born at the very beginning, in the first tiny fraction of a second after the birth of everything, before there were any stars at all. We call these the primordial black holes, and they are the most tantalizing members of the whole family, because they may explain some of the deepest mysteries in the sky, and because we have never, not once, actually found one. Let me be very clear about that from the start, in the honest spirit that has carried us all night. Primordial black holes are a hypothesis. They are an idea, a possibility, a thing the equations permit and that would tidily solve certain puzzles, but they have never been detected. No telescope has caught one. No signal has confirmed one. They may fill the universe in vast numbers, or they may not exist at all, and at present we genuinely do not know which. So, as I describe them, hold the whole picture lightly, the way you would hold a lovely idea that might yet turn out to be only an idea. That gentle uncertainty is part of what makes them such good company for a drifting mind at the end of a long day. Here is the thought behind them. In the ordinary way, to make a black hole, you need to gather a great deal of mass and crush it terribly tight, and in today's universe only the crush of a dying star or the slow gathering at a galaxy's heart can do that. Go back to the very first instant after the birth of the universe, and things were different. In that first moment, everything that now fills the vast cosmos was packed unimaginably close, hot and dense beyond any describing. The whole of creation squeezed into a space smaller than anything. And in that fierce early density, the matter was not spread perfectly smoothly. There were ripples in it, patches slightly denser than their surroundings, and the idea is that some of those denser patches may have been so tightly packed already, right from the start, they simply collapsed on the spot into black holes without ever needing a star to make them. Black holes born directly from the raw unevenness of the newborn universe in the first flicker of time before the first star had even begun to shine. That is what primordial would mean. Present from almost the very beginning. And because they would have formed from patches of every size, primordial black holes could come in a fantastic range of masses, including masses that no other process can make. A star cannot leave behind a black hole lighter than about 3 suns, because below that other forces hold the matter up. But a primordial black hole has no such flaw. One might weigh as much as a mountain, crushed into a space smaller than a single atom. One might weigh no more than a large asteroid. Some, in principle, could be tinier still, smaller and lighter than anything we would ever call a star's corpse. Dark specks scattered through space, each one a perfectly formed black hole in miniature, with a one-way door narrower than the smallest thing you could ever see. Imagine a black hole, the weight of a mountain and the size of an atom, drifting silently through the dark. That is the kind of strange creature the primordial idea allows. Why do scientists find this idea so appealing, when there is not yet a shred of direct evidence for it? Because of one of the great unsolved mysteries of the universe, a mystery called dark matter. When we weigh the galaxies by how their stars move, and weigh the great clusters of galaxies by how they hold together, we find again and again that there is far more gravity at work than the visible stuff can account for. There seems to be a great deal of unseen mass in the universe, several times more than all the glowing stars and gas put together, some invisible something whose gravity shapes the galaxies, but which gives off no light of its own. We call it dark matter, and despite decades of searching, we do not know what it is. And here is where the primordial black holes offer such a tempting answer. What if the dark matter is not some undiscovered particle at all, but simply vast numbers of small black holes, born in the first instant, scattered invisibly through every galaxy, adding up their gravity without ever adding any light? Would be a beautifully simple solution. The missing mass would just be black holes we cannot see, present since the beginning. Dark matter made of dark stars that were never stars. It is a lovely idea, and it may even be partly true, but honesty requires the full picture, so let us name the difficulties gently. Scientists have searched hard for these small black holes in clever ways. If space were full of them, they would now and then pass in front of distant stars and briefly brighten that starlight by their lensing, the bending we spoke of earlier, and by watching millions of stars for such tiny flickers, astronomers have been able to rule out primordial black holes as the whole of dark matter across wide ranges of possible masses. Those searches have closed many doors, but they have not closed all of them. There remain certain windows of mass, particularly around the weight of an asteroid, where small primordial black holes could still, in principle, hide in enough numbers to make up much of the dark matter without our current searches having caught them. So the idea is wounded, but not dead. It lives on in those narrow surviving windows, a hypothesis still very much worth taking seriously, still hunted, still unconfirmed. And so the primordial black hole holds a special and haunting place in our family portrait. It is the only member we have placed in the picture on the strength of an idea alone. The whispers we have found. The middle children we have finally heard. The giants we have weighed and even photographed. The monsters we have measured across 10 billion light years. But the tiny ancient ones, the firstborn, the possible dark matter, these we have never touched. They may be everywhere, threaded silently through the very room where you are resting, drifting through the earth itself now and then without a trace, each one a mountain crushed to an atom. Or they may be nowhere at all, a beautiful idea that the universe simply never used. To lie in the dark and wonder which is true, to know that this one question is genuinely open, that the answer is out there and simply not yet in our hands, is a fine and peaceful kind of wondering. Not every question has to be answered before sleep. Some are lovelier for being left open under the stars. There is one more idea we must gather in before we begin our long descent towards sleep, and it is perhaps the most surprising of all, because it turns the very definition of a black hole gently on its head. We have said over and over tonight that a black hole is a place from which nothing can escape, not even light, and that is true as far as the older understanding goes. But in the year 1974, a young physicist named Stephen Hawking, the same man who would later lose that friendly bet over Cygnus X-1, worked out something that astonished everyone, including himself. He found that black holes are not perfectly black after all. They glow ever so faintly. They leak. And, given enough time, unimaginable spans of time, they slowly evaporate away into nothing. How can that be if nothing escapes? The answer lives in the strange rules of the very small, the rules of the quantum world, and it is subtle. But let me try to give you a gentle picture of it. Empty space, it turns out, is not truly empty. Down at the smallest scales it seethes, ever so slightly, with pairs of particles that flicker into being and then, almost instantly, find each other again and vanish, borrowing a whisper of energy from the universe, and paying it back before anyone can notice. This constant faint fizzing happens everywhere, all the time, even in the deepest vacuum. Now imagine this happening right at the edge of a black hole, right at the one-way door. A pair of these fleeting particles flickers into being. one just outside the door and one just inside it. Ordinarily they would find each other again and vanish, cancelling out, as they always do. But here, one of them is already inside the horizon and it can never come back out. It is trapped. And so its partner, left alone outside, cannot cancel, and instead drifts away into space as a real particle, a faint mote of radiation carrying a little energy away from the black hole. To an outside observer, it looks exactly as though the black hole itself is very faintly glowing, giving off a thin, steady mist of particles from just outside its door. Mist is called Hawking radiation, and it means the black hole is slowly losing energy, and therefore slowly losing mass, and therefore slowly shrinking. Here is the part that ties the whole family together across time, from the tiniest primordial speck to the grandest monster, all on a single vast timeline. The rate at which a black hole glows and shrinks depends on its size, and in a way that runs exactly opposite to what you might guess. The smaller the black hole, the hotter it glows, and the faster it evaporates. The larger it is, the colder and fainter it glows, and the more unimaginably slowly it fades. A small black hole is like a small ember, giving up its heat quickly. A giant black hole is like a vast cold mountain, holding what it has for almost forever. So the smallest primordial black holes, if they exist, the little atom-sized ones, would glow relatively brightly and evaporate quickly, and some of the very smallest, born in the first instant of the universe, would have finished evaporating long ago, or would be reaching the end of their long fade right about now, finishing in a final faint flash as the last of their mass leaves them. This is, in fact, one of the ways astronomers have hunted for primordial black holes, by looking for the tiny flashes of their final evaporation. We have not found those flashes yet, another honest gap, another open thread. Turn now to the giants, and the timescale becomes almost incomprehensible in the other direction. A black hole the mass of the Sun would take vastly longer than the entire current age of the universe to evaporate, and a supermassive giant of millions or billions of suns would take a span of time so long that the numbers lose all meaning, a length of time so far beyond the present age of the cosmos that you could write the age of the universe over and over, endlessly, and still not approach it. These great black holes are, for all practical purposes, eternal on any scale we can feel. And yet, and this is the quietly astonishing thing, not truly eternal. Given enough time, given a future so distant that every star has long since burned out and gone cold, given a universe grown dark and empty and vastly older than it is now, even the greatest black holes would eventually, particle by faint particle, give themselves back to the void until nothing was left where they had been. There is a picture of the far, far future in which the last things remaining in the universe are the black holes, the final dark monuments of a cosmos gone quiet, and then even they, over spans of time beyond all imagining, slowly evaporate away, until at the very end there is only a thin, cold, evenly spread whisper of radiation drifting through an endless dark, the last faint warmth of everything that ever was. It is a solemn picture, And yet there is a strange peace in it too, a sense of a universe that does not hold on forever, that in the fullness of time lets even its heaviest things go. And this brings us, before we soften toward sleep, to the deepest and most honest gap of all, the one right at the center of every black hole, where our knowledge simply runs out. We have spoken all night of the event horizon, the door, and of the three numbers that describe a black hole from the outside. But what is actually at the very center, inside the door, at the heart of it all? The equations, pushed all the way in, give a strange and troubling answer. They say that all the mass collapses down to a single point of no size at all, a place where the density becomes infinite and the curving of space becomes infinite, a place we call the singularity. But an infinity in a physical theory is not really an answer. It is a sign that the theory has broken down, that it has been pushed past the edge of what it can describe. At the center of a black hole, our finest understanding of gravity and our finest understanding of the very small come into direct conflict, and neither one can tell us what is truly there. And so the honest truth is that we do not know what lies at the heart of a black hole. It is one of the very few places in all of nature where we can point and say, plainly, our known physics ends here, and something we do not yet understand begins. To find out, we would need a deeper theory than any we now possess, a way of joining gravity and the quantum world that no one has yet completed. It remains one of the great unfinished tasks of human thought. There is a related puzzle that troubled Hawking himself for much of his life, and it is worth naming gently, because it shows how alive these questions still are. If a black hole slowly evaporates away into that faint, featureless mist and eventually vanishes entirely, then what happens to all the information about everything that ever fell in? All the detail of every star, every atom, every whatever it was that crossed the door over the ages, seemingly erased by the no-hair theorem, seemingly lost forever when the black hole finishes its long fade. But the deep rules of the quantum world say that information should never truly be destroyed, only rearranged. So which is it? Which is it? Is the information truly lost in violation of everything we thought we knew, or is it somehow subtly carried out in the faint radiation after all, written in a code we cannot yet read? This is called the black hole information problem, and it is still not fully resolved. The finest minds in physics have wrestled with it for decades, and while there has been real progress, the last word has not been spoken. It is another of those places where you can lie in the dark and know with a strange comfort that the smartest people alive are still working on it, that the story is not finished, the universe still holds its secrets close. We have wandered a long way together tonight, out among the whispers and the giants and the monsters and the maybes, and now, slowly, let us begin to turn back toward home and toward rest. And a fair question to ask as we turn is this: do these strange dark objects have to do with us, here, small and warm and far away on our quiet blue world? It would be easy to think nothing at all. They are so distant, so vast, so utterly beyond our reach. and yet the truth is the opposite. The truth is that you would not be here to wonder about them at all if it were not, in part, for the great dying and gathering that black holes are bound up with. They are not merely far-off curiosities. They are woven into the story of how you came to exist. Think back to how the stellar black holes are born in the collapse and explosion of massive stars. That explosion, the supernova, does not only leave a black hole behind, does something else, something without which there would be no you and no Earth to hold you. Inside stars, and above all in the fury of their dying explosions, the heavier elements are forged. The simple universe began with almost nothing but the lightest gases, hydrogen and helium, and nothing else. Every heavier thing, every atom of the carbon in your body, the oxygen you are breathing right now, the iron in your blood, the calcium in your bones, the gold on a ring, the silver in a spoon, all of it was made inside stars and scattered out into space by the very deaths that also make black holes. The same violent ends that crush some cores into one-way doors, fling the rest outward as a sowing of new elements, seeds of everything that would ever be built. Our sun, our earth, the water in your glass, the atoms of your own hand resting on the blanket, all of it was gathered from the ashes of stars that lived and died long before the sun was born. You are made of that ash. And the black holes are the other half of that same story, the dark siblings of the elements that make you. Every time a black hole is born, a scattering of new matter is born with it, and some of that matter, somewhere, someday, becomes a world, and perhaps becomes a living thing that looks up and wonders. And there is more, for the giants may have shaped the very galaxies themselves. Remember that nearly every large galaxy has a supermassive black hole at its heart, and it is becoming clear that these giants and their galaxies grew up together, influencing one another over the ages. When a giant black hole feeds and blazes as a quasar, it pours out such tremendous energy that it can push and heat the gas across its whole galaxy, slowing or stopping the birth of new stars, sculpting how the galaxy grows. The dark heart at the center is not a passive thing. It has, over billions of years, helped to shape the great wheel of stars around it, perhaps helped to shape the size and the form of the Milky Way itself, the very galaxy in which our sun would one day light and our Earth would one day gather. So when you look up at the soft band of the Milky Way on a dark night, you may be looking at a shape that the dark giant at its center helped to carve. The black holes are not outside our story. They are near the root of it. Now let me answer the question I promised you at the very beginning, the one we set aside to return to at the end. What would it truly be like to fall into a black hole? We will never do it, of course, and would never wish to, and so we can wonder about it in perfect safety, the way you can wonder about the bottom of the sea from a warm, dry bed. And the answer holds one last surprise, a strange and beautiful contrast that ties our whole family of creatures together one final time. Turns out that the falling would be utterly different depending on which kind of black hole you fell into, the small or the great, and the difference is the opposite of what you might expect. fall toward a small black hole, one of the stellar whispers of a few suns, and the falling would be violent long before you ever reach the door. The reason is that gravity grows so fiercely stronger as you get closer to a small black hole that the pull on your feet, if you fell feet first, would be enormously greater than the pull on your head, simply because your feet would be a little nearer. The difference would stretch you, gently at first and then with terrible force, pulling you longer and thinner, while at the same time squeezing you narrower from the sides, until you were drawn out into a long, thin thread, like warm taffy pulled between two hands. Scientists, with the dark humor that sometimes visits even careful people, have given this a homely name. They call it spaghettification, the stretching of a falling body into a long, thin strand. Near a small black hole, you would be pulled apart this way long before you crossed the horizon. You would never even reach the door. The steep, savage climb of gravity around a small black hole would unmake you first. But fall toward a giant, one of the supermassive black holes of millions of suns, and everything changes, and here is the surprise. A giant black hole is so vast that its horizon, its one-way door, is enormously far from its center, and the pull of gravity near the door of a great black hole rises far more gently than near a small one. So gently, in fact, that at the horizon of a truly enormous black hole, the difference in pull between your head and your feet would be mild, no worse perhaps than a faint tug, nothing that would harm you at all. And so you could drift across the event horizon of a supermassive black hole, cross the one-way door, past the point from which no light and no signal and no living thing can ever return, and feel nothing. Nothing at all. No wall, no bump, no crossing sound, no sign. The stars behind you would still shine for a while. Your own hand would look exactly as it always had. You would have crossed the most absolute boundary in the universe, sealed your fate beyond any changing, and you would not even know the moment it happened. The door that can never be opened again would have swung shut behind you as softly as a breath, and only later, only slowly, would you come to understand that every direction you could now choose to move led inward, that the center had become your future, that there was no longer any such thing as back. There is something almost unbearably gentle in that, and it is where I would like to leave the science, on this quiet contrast. Two ways to fall, the same ending, opposite in their tenderness. The small black hole tears you apart before you arrive, all violence and warning. The great one lets you pass its threshold without a whisper, all silence and calm. Same fate. Opposite gentleness. And in that strange pairing there is something, I think, that speaks softly to the whole of tonight, to the whole of this dark and beautiful family we have walked among, from the smallest whisper to the grandest monster. The universe holds terrors, yes, places where gravity has won so completely that nothing at all comes back. And yet, even at the edge of the most absolute of them, there can be a stillness so deep that you would not feel yourself crossing over. Even there, in the last and darkest place, there can be peace. There is a last strangeness about falling into a black hole that we have not yet touched, and it is the strangest of all because it concerns not space but time. We have spoken all night as though time were simply the steady background against which everything happens, the same for everyone, everywhere, ticking on at one rate for us all. One of the deepest lessons of Einstein's work is that this is not so. Time does not flow at the same rate everywhere. Gravity slows it down. The stronger the gravity, the slower time runs, and near the door of a black hole, where gravity grows without limit, time slows toward a stop. This is not a trick of measurement or a flaw in our clocks. It is real. Time itself, the very passing of moments, stretches and slows near a black hole. Let me give you the picture that makes it felt, and it is one of the most haunting in all of physics. Imagine you are watching from a safe distance as a friend falls slowly toward a great black hole, carrying a bright lantern so you can follow them down. As they drift closer to the horizon, closer to the one-way door, you would see something eerie begin to happen. Their fall would appear to slow. Not because they are slowing in their own experience, but because, from where you watch, their time is running ever more slowly compared to yours. Closer they drift to the door, the slower they seem to move, the more they linger, until at last, as they approach the very edge of the horizon, they would appear to you to freeze, to hang there, suspended, almost motionless, right at the threshold, taking longer and longer and longer to move even the smallest distance. And their lantern, as they neared the door, would grow dimmer, and its light would slowly redden and fade, sliding down through the colours and then away past all seeing, until it dimmed into darkness. From the outside, your friend would never quite be seen to cross the door at all. They would seem to slow and redden and fade and hang forever at the edge, a fading ghost frozen at the threshold, growing dimmer through the ages until they slipped from view entirely. But here is the part that turns the mind gently inside out. From your friend's own point of view, nothing of the kind would happen. For them, time would run perfectly normally, as it always has, 1 second following the next. They would not feel themselves slow. They would not hang frozen at the door. They would simply fall smoothly and steadily and cross the horizon at an ordinary moment, feeling nothing unusual as they passed it, exactly as we described before, and continue on inward, all in a matter of moments by their own clock. The freezing at the door exists only for the one watching from outside. The falling continues, ordinary and swift, for the one who falls. Two people, the same event, and two utterly different stories of it, both completely true. One sees an eternal slow fading at the threshold. The other simply falls through and is gone. Time itself has split the story in two. Sit with how deep that is. It means there is no single answer to the simple seeming question, how long does it take to fall into a black hole? It depends entirely on who is asking and where they stand. For the faller, moments. For the distant watcher, an eternity of slow fading. Time is not the fixed and universal thing we feel it to be in our ordinary lives. Bends like space near great masses, and near the greatest masses of all. It bends so far that two honest observers can no longer agree on what happened or when. The universe does not keep a single clock. It keeps a clock for every place and every path, and near a black hole those clocks fall wildly out of step with one another. There is even a strange gentleness hidden in this, if you look for it. That fading ghost at the threshold, the friend who seems to hang forever at the edge, never quite crossing, growing slowly dimmer and redder through the ages, is in a way still present to the outside universe long after they have, from their own side, fallen through and gone. The black hole holds their image at its door, fading but lingering for a very long time. Nothing is ever quite abruptly lost to a black hole seen from outside. It slows and reddens and fades and lingers at the threshold, easing out of the universe gradually rather than all at once. Even the door, the most final boundary there is, does not slam. Closes slowly over ages in a long, soft dimming. And perhaps that is a fitting last strangeness to carry towards sleep, that even here, even at the edge of the most absolute thing in all of creation, the universe does not hurry and does not wrench, but only slows and softens and fades, as gently as the day now fading behind you into night. There is a thread running through everything we have said tonight that I would like to pull on gently for a while, because it is soothing to think about, and because it lies underneath every number I have given you. Every time I have told you how far away a black hole sits, 27,000 light-years to the center of our galaxy, 55 million light-years to the giant in Messier 87, 10 billion light-years to the monster in Ton 618, I have been telling you something quiet and profound about time as much as about distance. Because to look far out into space is always, without exception, to look back into the past. And I want to walk slowly through why that is, and how we ever came to measure such distances at all, because the measuring is itself one of the most patient and beautiful things our species has ever done. Start with the simple fact at the root of it. Light is fast, faster than anything, but it is not infinitely fast. It takes time to travel. Light from the sun takes about 8 minutes to reach us, so the sunlight warming your window is always 8 minutes old, and if the sun were to vanish, you would go on seeing it shine for 8 more minutes before the sky went dark. That is a small delay, easy to hold. But now stretch it. The light from the next nearest star takes more than 4 years to reach us, so you never see that star as it is, only as it was 4 years ago. And the further out you look, the deeper into the past you see. This is why we measure the great distances in light years, a light year being simply the distance that light travels in 1 year, and it is a measure of time folded into a measure of space. When I say the center of our galaxy is 27,000 light-years away, I am telling you that its light is 27,000 years old by the time it reaches your eye. You are seeing the heart of the Milky Way not as it is tonight, but as it was when the last ice age still gripped the world. So when we look at TON 618, that monster 10 billion light years off, we are not seeing it as it is now. We are seeing it as it was 10 billion years ago, when the universe was young and our sun did not yet exist. We can never see it as it is today. Its light of today will not arrive for another 10 billion years, long after our sun has died. Every telescope, in this sense, is a kind of time machine, and it can only look backward, never forward, and the farther it looks, the older the news it brings. The night sky is not a picture of the universe as it is. It is a picture of the universe as it was, every point in it showing a different moment of the past, the near stars young by only years, the far galaxies ancient by billions of years, all their different pasts gathered together into the single quiet image we call the night. There is something deeply restful in that thought. When you lie back and look up, you are not looking at the present at all. You are looking at a great layered memory, the whole history of the cosmos arranged by distance, the past made visible, spread out overhead like the pages of a book left open to every chapter at once. But how, you might fairly wonder, do we ever measure such distances in the first place? How can anyone possibly know that a thing is 27,000 light-years away, or 10 billion? We cannot stretch a tape measure across the void. And yet, step by patient step, astronomers have built a ladder of methods, each one reaching a little farther than the last, and the building of that ladder is one of the quiet triumphs of human thought. Let me show you the first few rungs, because they are simpler than you might fear, and lovely to hold in the mind as you drift. The first rung is a trick you use every day without noticing, the same trick your two eyes use to judge how far away things are. Hold up one finger at arm's length and look at it first with one eye closed, then the other. The finger seems to jump against the background. That jump is because your two eyes see it from slightly different positions, and the nearer the finger, the bigger the jump. Astronomers do exactly this with the stars, only their two eyes are the Earth itself in two different places in its orbit, 6 months apart, on opposite sides of the Sun. They measure a nearby star's tiny jump against the far background, and from the size of that jump, they work out the distance by plane geometry, the same geometry a surveyor uses to measure across a river without crossing it. This is called parallax, and it is the firmest, most direct rung on the whole ladder, the one that needs no assumptions at all, only careful measurement and patience. Parallax reaches only so far. For stars too distant to show any measurable jump, astronomers climb to the next rung, and it is a clever one. There is a special kind of star that pulses, brightening and dimming in a steady rhythm, swelling and shrinking like a slowly beating heart. And more than a century ago, a careful astronomer named Henrietta Leavitt, studying thousands of these pulsing stars, discovered something wonderful about them. The brighter the star truly is, the slower it pulses, and the rhythm and the true brightness are locked together by a fixed rule. This means that if you simply watch such a star and time its pulse, you can know how bright it truly is. And once you know how bright a thing truly is, and you see how bright it merely appears from here, the difference tells you the distance, in exactly the way a candle that looks dim tells you it must be far, while the same candle looking bright tells you it is near. These pulsing stars became measuring candles scattered through space, letting us reach across distances that parallax could never touch, out to other galaxies entirely. It was by these very stars that we first learned that the faint smudges in the sky were not clouds within our own galaxy at all, but whole other galaxies unthinkably far away, each one a wheel of billions of stars in its own right. And there is a rung higher still for the farthest reaches, and it rests on a different candle, the brightest of all. When certain stars die in a particular kind of explosion, they all flare to very nearly the same true brightness, a known and reliable brilliance, so that a single such explosion can serve as a standard candle visible clear across the universe. By watching for these explosions in distant galaxies and measuring how bright they appear, astronomers can measure distances of billions of light years. And there is one more tool for the very farthest things, which rests on the fact that the universe is expanding, every distant galaxy drifting away from us, and the farther a galaxy is, faster it recedes, and the faster it recedes, the more its light is stretched toward the red end of the rainbow, the way the pitch of a receding siren drops. By measuring that reddening, that stretching of the light, astronomers can gauge the distance to the most remote objects of all, out to quasars like TON 618, 10 billion light-years and more into the deep. Rung upon rung, candle beyond candle, the ladder climbs, each method calibrated against the one below it, until from the humble jump of a nearby star, we have built our way out to the very edge of the visible universe. So the next time a number lands in your mind tonight, a distance in light years, a weight in suns, remember that it did not come easily, and it did not come by guessing. It came from generations of patient people, measuring tiny jumps and timing slow pulses and reading the colors of ancient light, building carefully upon one another's work across a century and more, until we could say with real and earned confidence how far and how heavy and how old these dark things are. There is a great and quiet dignity in that, in the slow, honest accumulation of it. We are a small and short-lived creature on a minor world, and yet, by care and patience and the passing of knowledge from hand to hand, we have measured the distances to monsters 10 billion years in the past. That we can do such a thing at all is, to me, as wondrous as the monsters themselves. Let us do something restful now. Let us gather the whole family back together in the mind one more time, and lay them side by side from smallest to largest, and simply feel the range of them. There is a deep calm in returning to a thing you already know, in walking a path a second time now that its turns are familiar, and the scale of these objects is so vast that it rewards being felt more than once from more than one angle. So breathe slowly, and let us line them up under the stars. Begin with the smallest we are sure of, the stellar whispers. A black hole of about 3 times the mass of the sun, the lightest that a dying star can leave behind. Crush 3 suns down until gravity wins, and the one-way door that opens is only about 10 or 12 miles across. 10 or 12 miles. You could drive around the whole of it, the entire outer edge of a thing that holds 3 suns, in the time it takes to drive across a small city and back. Hold that. A weight of 3 suns in a circle you could walk the rim of in an afternoon. That is the smallest of the real ones, and it is already past all ordinary understanding, and it is the gentlest member of the whole clan. Now step up to Cygnus X-1, the first one we ever found, about 21 times the mass of the Sun. Its door is wider, perhaps 80 or 90 miles across, still small enough to sit unnoticed within the space of a single country, and yet it holds 21 suns, and it sits 7,000 light-years away, quietly pulling the wind off the great blue star that dances around it. Step up again to the black holes that the great detectors hear colliding, the ones of 30 and 60 and 80 suns, and to the middle child of 142 suns born in that collision in 2019. With each step the door grows wider, the weight grows heavier, but we have not yet even begun to approach the giants. We are still among the whispers and the middle children, still on the near shore of the truly vast. Now cross to the giants, and feel the ground fall away beneath you. Sagittarius, a star, the quiet monster at the center of our own galaxy, 4 million times the mass of the Sun. Its door is not miles across now, but millions of miles across, wider than the Sun itself, wide enough that our own star, that great engine that dwarfs the Earth 1 million times over, would be a small thing beside it. 4 million suns in a single dark point, 27,000 light-years down the long road towards Sagittarius. And even that is only a middling giant. Step up once more to M87 star, the one we photographed first, 6.5 billion times the mass of the Sun. Its door would swallow our entire solar system, all the planets out to the farthest cold and distant one, and still have room to spare. Light itself, which crosses from the Sun to the Earth in 8 minutes, would need most of a day merely to travel across the width of that single black hole's shadow. And that door sits 55 million light-years away, and we have seen it, an orange ring of fire around a circle of dark, an actual photograph of an actual thing that vast. And then, at the very far end, the monster. Ton 618. Somewhere between 40 billion and 66 billion times the mass of the Sun, we are not sure which, and it hardly matters at this scale, for either number is beyond the reach of feeling. A single black hole that may weigh as much as all the stars of an entire galaxy combined. Its door stretches many times the width of our whole solar system, a boundary so vast that if you set out to cross it at the speed of a fast spacecraft, a journey to it would consume not years but ages. And it sits 10 billion light-years away, its blazing light 10 billion years old, showing us a thing as it was before the Earth was formed. From the whisper you could walk the rim of in an afternoon to the monster whose door light needs the better part of a day to cross. This single family of objects spans a range of sizes so enormous that the smallest and the largest scarcely seem to belong to the same universe, let alone the same kind of thing. And yet they do. every one of them is a place where gravity has won. Everyone is built from those same three plane numbers: mass and spin and charge. Everyone is a one-way door in the fabric of space. There is one more way to feel the scale, and it is my favourite, so let us end our regathering with it. Take our own sun again, that vast ball you could pour more than 1,000,000 Earths into. To turn it into a black hole, we said you would crush it down to about 4 miles across. Now hold that image, the whole sun squeezed to a little dark ball 4 miles wide, and set it beside the door of Ton 618, that monster at the far end. If the crushed sun were the size of a single grain of sand, then the door of the monster, to the same scale, would be wider than a great city. That is the range we are speaking of. A grain of sand and a city, and both of them the very same kind of object, both of them black holes, both of them silent and dark and drifting somewhere in the deep tonight. When people say the universe is large, this is part of what they mean, and it is a largeness that has room in it not only for great distances, but for great differences of scale within a single family of things, a range so wide that the mind can only take it in a piece at a time, which is exactly why we have taken it slowly and more than once, and why there is no shame in letting most of it wash gently past. You are not meant to hold it all at once. No one can. You are only meant to feel, now and then, the edge of how vast it is, and to rest inside that feeling rather than against it. There is a question that the single question of tonight naturally opens into, and it is one people often ask in a hushed voice, half hoping the answer will be small and comforting. How many of these things are there? If black holes are drifting through the universe, how many and how near? Let us sit with that gently, because the true answer is larger than most people expect, and yet, held rightly, it is not a frightening thing at all, but a strangely companionable one. Consider only our own galaxy, the Milky Way, and only the stellar black holes, the whispers born from dying stars. Astronomers estimate that our galaxy holds something on the order of 100 million of them. 100 million black holes scattered through the one galaxy we call home, most of them drifting alone in the dark between the stars, invisible, silent, giving off no light, betraying themselves to no one. For every one we have found, by its glowing disk or its dancing companion star, there are countless others we have never seen and never will, wandering the spaces between the stars like dark seeds sown through the whole vast wheel. And ours is only one galaxy among perhaps 2 trillion galaxies in the visible universe, each with its own uncounted multitude of black holes, and each with its own giant anchored at its heart. The true number, across all of it, is beyond any counting, a number with no useful name, a number that means simply past all imagining many. And yet notice how quiet they all are. 100 million black holes in our galaxy, and not one of them troubles us in the slightest. They do not roam about swallowing worlds. They do not drift toward us with hungry intent. A black hole is not a cosmic vacuum cleaner pulling in everything around it, whatever the stories suggest. Its gravity, at a distance, is no different from the gravity of any other object of the same mass. If our own sun were somehow, this instant, replaced by a black hole of exactly the same weight, the Earth would not be pulled in at all. It would go on circling in the very same orbit, in the very same year, as though nothing had changed, except that the light and the warmth would be gone and the sky would fall dark. The black hole would not reach out for us. Gravity does not grow greedy simply because a thing is dark. The danger of a black hole lies only in coming very close to it, in crossing near that one-way door, and the doors, for all their number, are tiny compared to the vast empty spaces between the stars. The nearest known black hole to the Earth sits well over 1,000 light-years away, which is to say, unthinkably far by any human measure, so far that its presence means precisely nothing for the safety of your rest tonight. The black holes are many, and they are near in the way cosmic things are near, which is to say, not near at all. You may hold their great number in your mind without the smallest fear. They are simply out there, being what they are, in the enormous dark, and the enormous dark has room for all of them and for us besides, with distance to spare. Think of them, if it comforts you, as a kind of quiet population sharing the galaxy with us, most of them the long-cooled corpses of stars that lived and shone and died before our sun was born. Each one was, once, a blazing giant, pouring out light for millions of years, and each one, in its dying, sowed a little of the matter that would go on to make new stars and worlds, and perhaps, somewhere, new life. They are the elders of the galaxy, in a sense, the ones who went first, who lived their bright lives and then folded quietly down into the dark, leaving behind both their scattered ashes and their silent doors. When you look up toward the band of the Milky Way tonight, you are looking across a wheel that holds 100 million of these old dark elders, resting between the living stars, and you need not fear a single one of them. They are simply keeping the long dark with us, at a great and gentle distance, the way the oldest trees keep a forest, having grown and given and gone still. And here is a thought to carry towards sleep, one that folds the near and the far together. Giant at the centre of our own galaxy, Sagittarius, a star, 4 million suns of silent dark, is not a stranger to you. You are bound to it. This very moment, without any feeling of motion at all, you and the Earth and the Sun are sweeping in a great slow circle around that dark giant, carried along at 500,000 miles an hour on an orbit so vast it takes more than 200 million years to complete. You have been circling it your whole life. Every person who has ever lived has spent their entire life circling it, and in all of human history we have not gone even a fifth of the way around once. The dark giant holds you gently at a distance of 27,000 light-years and turns you slowly through the ages and asks nothing of you, and you never feel it, and you are perfectly safe. There is a black hole at the center of your life, in the most literal sense, and it has cradled you and everyone you love in a slow, wide circle since before you were born, and it will go on cradling those who come after, long after we are all asleep for good. That is not a thing to fear. That, I think, is a thing to rest inside. Let us drift now, slowly, away from the hard edges of measurement and towards something softer, the way a river widens and slows as it nears the sea. We have spent the night among numbers, and the numbers have been vast, and now I would like simply to wander among the meanings of them for a while, at an easy pace, with nothing left to prove. So let your attention loosen. There is nothing more to learn tonight. There is only wondering left, and wondering is the gentlest thing the mind can do. Think first about time, not the small time of days and years, but the great deep time in which the black holes live. We spoke of how the giants will one day, in the unimaginably distant future, slowly evaporate away, giving themselves back to the dark particle by faint particle. To feel what that means, you have to let your sense of time stretch far past anything a human life can hold, and there is a strange peace in that stretching. Our whole recorded history, every war and every song and every name that was ever written down, fills only a few thousand years. The whole span of life on Earth fills a few billion. The universe itself, so far, has lasted a little under 14 billion years. These are numbers we can at least begin to gesture at. But the lifetime of a great black hole, the time it would take one of the giants to fade completely away, is longer than the current age of the universe. Not by a little, not by 1,000 times, by 1,000,000 times, but by a factor so enormous that you could write out the age of the universe and then follow it with so many zeros that the mind simply lets go. Compared to the life of a supermassive black hole, the entire history of the universe until now is less than the first blink of the first instant. And that means something quietly beautiful. It means that the black holes are, in every sense that matters to us, the most patient things in all of creation. The stars burn and die in mere millions or billions of years, brief candles by the measure of the cosmos. The galaxies wheel and change, and eventually run out of the gas that makes new stars, and their light slowly reddens and dims. The black holes remain, long after the last star has flickered out, long after the galaxies have gone dark and cold, long after everything we would recognize as the universe has faded. In the deep future, when the sky holds no more starlight anywhere, when the cosmos has grown vast and empty and utterly dark, the black holes will still be there, the last great structures, final dark monuments, sitting patiently in the endless night, giving off only the faintest imaginable whisper of hawking glow. They will outlast the stars by a margin beyond all telling. They are the universe's long memory, the things that endure when all else has gone. And then, at the very, very end, even they will go. That is the part I find most moving of all. Even the most patient things are not truly forever. Given time enough, and there will be time enough, more than enough, endlessly more than enough, even the greatest black holes will finish their slow evaporation and simply cease to be, winking out one by one across ages that dwarf all the ages that came before. And after the last of them has gone, the universe would settle into a final stillness, a thin, cold, even mist of radiation spread through an infinite dark, no stars, no galaxies, no black holes, nothing to mark one place from another, or one moment from the next. It sounds lonely, written that way. But I have never been able to feel it as lonely, only as calm. There is a kind of gentleness in a universe that does not clutch at its own things forever, that lets even the heaviest and most enduring of them go soft into the dark at last. Everything rests, in the end. Even the black holes. Even gravity, having won everywhere, at last has nothing left to win and falls quiet. You do not need to fear any of this, of course, for it lies so far ahead that the word future hardly reaches it. The sun will warm the earth for billions of years yet. The stars will fill the sky for ages beyond ages. Not one of us, nor our children's children's children out to the 1000th generation and far beyond, will ever see the sky begin to dim. The deep future is not a thing that is coming for you. It is simply a thing that is true, out there at the far end of time, the way the far side of the ocean is true, even though you will never swim to it. And there is comfort in knowing it, I think, rather than fear. Places the small worries of a single night in their proper size. Whatever weighs on you tonight, whatever you carry to your pillow, is unfolding inside a universe so vast in time and space that it holds room for 100 million black holes in our galaxy alone, and ages so long that the giants themselves are only passing things. Your troubles are real, and they matter, and they are also, held against this backdrop, wonderfully, mercifully small. The cosmos is very large, and very old, and very patient, and it has carried far heavier things than your worries through far longer nights than this one, and let them in time grow quiet and rest. It can carry yours too. It is already carrying them. You have only to let it. Let us stay here a while, in this soft and open place, and think about smallness, because I know the word can frighten people, and I would like to take the fear out of it, gently, before you sleep. When you first truly feel the scale of the things we have talked about tonight, the millions of suns, the 10 billion years of travel, the 100 million dark elders in our galaxy alone, can make a person feel very small, and small can feel like nothing, and nothing can feel like a cold and lonely thing. But I have come to believe that this is a misreading of the feeling, and that if you sit with it long enough, patiently, in the dark, smallness turns into something else entirely, something warm. Yes, you are small. On the scale of a black hole, you are less than a speck. On the scale of the galaxy, the entire Earth is less than a speck, and the sun that holds it is one ordinary star among hundreds of billions, far out on a quiet arm of the wheel. On the scale of the whole universe, the entire Milky Way is one galaxy among perhaps 2 trillion, a single grain in an ocean of grains. There is no way to make yourself large against that backdrop. The numbers will not allow it, and it would be a kind of lie to try. But here is the turn, and I want you to feel it rather than merely hear it. To be small is not the same as to be nothing. To be small is to belong to something immense. And that belonging is not a diminishment. It is the opposite. It is the largest thing you will ever be part of. Consider what you are actually made of, which we touched on earlier, and which is worth returning to now, softly, as a lullaby returns to its opening line. The atoms in your body, the iron in your blood that carries your every breath, the calcium that holds you upright, the carbon that forms the very frame of you, every one of those atoms was forged inside a star, in the crush and fire of a stellar heart, or in the violent brilliance of a dying star's explosion, the same kind of explosion that leaves black holes behind. You are not separate from the vast story we have told tonight. You are made of its chapters. The dying of ancient stars which sowed the black holes through the galaxy also sowed the very stuff of you. You are, in the most literal and unsentimental way, a piece of the universe that has gathered itself together for a little while into a shape that can look up and wonder about the rest. When you lie there tonight and think about a black hole 10 billion light years away, something remarkable is happening. The universe is contemplating itself. A handful of stardust, arranged into a mind, is turning its attention back toward the great dark hole it came from. That is not nothing. That is one of the rarest and most extraordinary things there is. And so your smallness held rightly is not a cause for loneliness, but for a strange and steady companionship. You are not a stranger looking in at a universe that has nothing to do with you. You are a part of it, born of it, made of its oldest materials, held in the slow circle of its gravity, kept warm by one of its stars. The same laws that shape the black holes shape the falling of your own breath toward stillness right now. The same gravity that won so completely at the center of those dark doors is the gentle weight that holds you to your bed tonight, that keeps your body resting easy against the mattress, that will hold you softly all night long. You are not outside all of this, peering in. You are inside it, held by it, one small, warm, living part of an immense and ancient and patient whole. And a part is never truly alone, however small it is, because it is joined at every edge to everything else. There is an old and simple comfort in feeling yourself a part of something far larger than yourself, and it is a comfort that does not depend on understanding all the numbers, or remembering any of the names, or holding on to a single fact from tonight. You can let all of it go now, all the Schwarzschild and the Kerr, all the light years and the suns, every figure and every discovery, and keep only this, that you are made of stars, that you are held gently in a slow, wide circle by a dark and patient giant that means you no harm, that you are one small living piece of a cosmos so vast and so old that it has room for every wonder and every fear, and time enough to let them all, in the end, grow quiet. You belong here. As small as you are, in a universe as large as this, you belong here completely, and always have, and always will. There was never a moment when you did not belong. The stars made you, and the galaxy holds you, and the long dark keeps you, and there is nothing in any of it that you need to be afraid of tonight. Let your breathing slow a little now, if it has not already, and let us think softly about the dark itself, because we have spent the whole night in it, and I would like to leave you at peace with it. We are taught, somewhere young, to be a little afraid of the dark, and of black holes most of all, those places of absolute darkness where even light gives up. The more time you spend among these things, the more the fear thins away, and something gentler takes its place. The dark, it turns out, is not empty. It is not a nothing waiting to swallow us. It is full. It is where the stars live, and the galaxies, and the great slow wheels of them turning. It is where the oldest light in the universe still travels. It is where you came from, and where everything you love came from, and it has been nothing but generous all this time in the making of us. Think of the one-way door again, the event horizon, that most final of all boundaries, and remember the strange gentleness we found there at the end. We tend to imagine it as the most fearsome thing in the cosmos, a place of terror, a point of no return. And in one sense it is. But recall what we learned about falling into a great black hole. That you could cross that most absolute of all thresholds, past the point beyond which there is no returning, and feel nothing at all. No violence, no pain, no jolt, no sign. Only a quiet you would not even notice, a boundary crossed as softly as sleep comes. There is something in that image that has always struck me as more tender than frightening. The universe's most absolute door, and it can be passed without a whisper. The most final thing there is, and it can be as gentle as a breath let go. And is that not, in a way, a little like sleep itself? You are lying there now, awake, holding the day behind you and the strange journey of tonight, and somewhere ahead of you, not far, is a threshold you cross every single night, the threshold into sleep. You never feel the moment you cross it. No one ever does. You cannot point to the instant you fell asleep. The exact heartbeat when waking became dreaming. It happened softly, without a sign, a boundary passed without your noticing, and on the other side is rest. Every night of your life you have drifted across that quiet door, and every morning you have returned, and there was never anything to fear in the crossing. Tonight will be no different. When it comes, you will not feel it. You will simply be resting on the far side, carried, the way the whole earth is carried in its slow circle, the way everything is carried, gently, whether it feels the carrying or not. To rest beneath the infinite is not to be lost in it. It is to be held by it. To yourself, if you like, lying out under a truly dark sky, the whole band of the Milky Way spilled overhead, more stars than you could ever count, and somewhere among them, unseen, quiet giants, and the drifting elders, and all the dark doors of the family we met tonight. And you, small and warm, lying beneath all of it, breathing slowly. You are not falling into that great dark. You are resting under it, the way a child rests under a warm, heavy blanket, the way the ground rests under the wide night sky. The immensity above you is not reaching down to take you. It is simply there, ancient and patient and vast, keeping the long watch it has always kept, while you, its small living part, made of its oldest stars, held in its slow gravity, let yourself grow heavy and still. There is nothing you need to do. There is nowhere you need to be. There is no number to remember and no question to answer. The universe has been getting along for nearly 14 billion years, and it will go on getting along patiently, whether you stay awake to watch it or not. You are allowed to rest. You are meant to rest. The great dark will keep turning, gentle and sure, and it does not need your worry to hold itself together, and it never did. So let the last of the day go now. Let the small worries loosen their grip, one by one, the way the giant at our galaxy's centre has, over the ages, let go of nearly everything around it, and settled into its long, quiet rest. Let your shoulders grow heavy. Let your hands grow soft. The weight of your own body settle into whatever holds you, and feel, if you can, that same gentle gravity that rules the black holes and the stars, and the whole turning wheel holding you too, softly, exactly where you are, asking nothing, keeping you safe through the dark. You are a small, warm part of something vast and old and kind. And it is time now to rest inside it. And so, as the night draws in around us, let us circle gently back to where we began. Remember the field. Remember how we started, lying back in the cool grass, far from any town, with the whole river of the Milky Way spilled across the sky above us, more stars than anyone could ever count, the air still, the dark, soft and close. That is where our journey started, under that spilled river of light, wondering about the unseen things hidden within it. And now, after all our wandering out to the monsters and back, we return to that same field, that same sky, that same quiet patch of grass, only now we know a little more about what we are lying beneath. We know now that somewhere in that great spilled river overhead, 27,000 light years down the long road toward the constellation of the Archer, a dark and patient giant sits at the very center of it all. 4 million suns of silent gravity holding the whole wheel together, turning us slowly through the ages while we lie here and breathe. We know that scattered through that same river are 100 million dark elders, the quiet corpses of ancient stars, resting between the living lights, harming no one, keeping the long dark with us at a great and gentle distance. We know that the very atoms of the grass beneath us, and of the hands folded on our chest, and of the breath moving softly in and out, were forged in stars that died long ago, the same dying that leaves the dark doors behind. We are lying in a field made of stardust, beneath a sky full of quiet giants, held in a slow wide circle by the darkest and most patient thing there is, and there is nothing here, in any of it, that means us any harm. There never was. The journey that began beneath the stars has circled back to where it started, and you are still here, still breathing, still small, and still warm, still held. That is the whole of it. That is all you need to carry from tonight. The names, not the numbers, not a single fact if you would rather let them all drift away. only the feeling of lying safe beneath something vast and old and kind, and knowing now a little of what it is. If this quiet hour has brought you any ease, you might rest with us again some other night, when the day has been long and the mind will not go still. There will always be another question to wander toward, slowly, together, and always the same soft dark to wander through. And if you know someone else who lies awake, someone who could use a calm voice and a slow story to carry them towards sleep, you might share this quiet moment with them too. But that is for another day. There is nothing left to do tonight. For now, let your breathing slow. Let each breath grow a little longer than the last, and a little softer. Let your body grow heavy, from the crown of your head down through your shoulders, down through your arms and your hands, down through your chest and your legs, all the way to your feet, every part of you growing warm and heavy and still. Let the field hold you. The gravity that rules the stars hold you gently, exactly where you are. There is no threshold ahead of you to fear. You will cross into sleep the way everything crosses the softest doors, without a sign, without a sound, without ever feeling the moment you passed over. And on the far side, there is only rest. You are a small, warm part of an immense and ancient universe, and it has carried you safely to this very moment, and it will carry you gently through the night. Rest now. Let go. The stars will keep their long watch, and the dark will keep turning, slow and sure, and you have nothing left to do but sleep. Good night.